GCE Advanced Level Chemistry Practical Series Experiment number 3. Handling glassware and triple beam balance. In this experiment, we are going to observe the different types of glassware that we find in the lab, and we are going to learn about for what purposes we will be using each of these different lab equipment, and we are going to learn about how to handle this glassware, how to clean this glassware, as well as the precautionary measures that revolve around each of these different glassware. Apart from that, we will be observing how we can use the triple beam balance as well. Students, what we have in front of us are different types of glassware that we will be using for today's experiment. Each of these different glassware is used for a specific purpose, and when you are handling them, you need to have the knowledge to handle them properly. So, in this experiment, we aim to provide you with the necessary knowledge to handle each of these different glassware correctly. Apart from that, we will also be looking into how to clean them as well, and we'll also be mentioning the precautionary measures you should be taking when handling each of these different glassware. When it comes to cleaning glassware, we will always use a liquid detergent to first wash the inside as well as the outside of the glassware, and then you're going to wash the glassware at least 3 times with tap water so that all of the detergent is washed off of the surface of the glassware, and afterwards we are going to be washing it at least 3 times or rinsing it at least 3 times with distilled water. Sometimes when you are carrying out this washing process, you might come across certain solid materials that are stuck on the surface of this glassware. At that point, you can include or you can add some potassium hydroxide and ethyl alcohol or ethanol and let it soak for a while, and then you can move on to wash it again with water and then with distilled water. Even after that, if the solid residue is still remaining in the glassware, you can use a little bit of HCl to remove the solid residue that is still present in the glassware. After removing this solid residue, you can proceed to wash it with tap water and then with distilled water. Now students, apart from using a liquid detergent to wash the glassware, you should be very careful not to scrub the glassware using a solid material. You can use a soft sponge, but you should not be using a solid wire brush or some sort of solid wire material to scrub the glassware. Especially when cleaning volumetric glassware, you have to take extra caution, because if you even use a test tube brush or a brush that is used to clean test tubes to clean the internals of a volumetric glassware, it might damage the internal walls of the volumetric glassware, and it will no longer be properly calibrated if some sort of damage happens to the internal walls of volumetric glassware. Volumetric glassware are glassware that we have over here or that we use to precisely measure different volumes of different reagents. If they are damaged, at that point they are not going to be providing us precise measurements, or their measurements are not going to be very accurate. So therefore, when cleaning glassware, you can use a soft sponge. When cleaning test tubes and boiling tubes, you can use a test tube cleaner or a small brush to clean the test tube. However, you should not be using any hard materials when cleaning volumetric glassware. When you're cleaning volumetric glassware, take precaution not to use any hard materials or any materials that are hard on the glassware should not be used when cleaning volumetric equipment. Apart from that, after washing your glassware, you should allow it to dry in a drying cabinet. You can place it in a drying cabinet set at a temperature of around 40 degrees or 50 degrees Celsius. And then when you are drying it, if you want to dry it a little bit faster, you can wash the internal surface with a little bit of acetone. Acetone will speed up the drying process, so therefore you can use the glassware in a shorter span of time. But keep in mind, students, when we use a drying cabinet, you have to take precaution not to include any volumetric glassware in the drying cabinet. Volumetric glassware will have different markings indicating different volumes, and some of these markings are going to come off under extreme heat. So therefore, it is best to not place any volumetric glassware in the drying cabinet. You can dry the different types of volumetric glassware in air without placing them in a drying cabinet. So students, in summary, when you're cleaning these different types of glassware, you should be using liquid detergent to wash both the internal and the external surfaces of the glassware. You should be rinsing the glassware at least 3 times with tap water and then at least 3 more times with distilled water. When you are washing glassware, you can use a soft sponge. Do not use hard washing materials like scrubbing material or different types of wire meshes should not be used to clean glassware, because it might introduce some scratches or different types of damages to the glassware. Test tubes can be used using a test tube cleaner, a small brush that can be inserted into the test tube. However, you should not be using those kind of brushes with hard bristles to clean volumetric glassware such as pipettes, burettes, measuring cylinders, volumetric flasks, and so on. So after taking a look at how we wash this glassware, when it comes to drying, one of the ways in which you can dry a washed glassware faster is by adding a little bit of acetone. When you add a little bit of acetone and you coat the entire surface with the acetone and then remove the acetone that is in the container, after a while the glassware is going to be dry. As acetone evaporates, glassware will dry faster. Apart from that, you can place the glassware in a drying cabinet. However, you should not be placing volumetric glassware in drying cabinets. So after learning how to clean this glassware, we can now move on to learning how to handle each of these different types of glassware. Let's start with test tubes and boiling tubes. In this part of our experiment, we are going to learn how to use test tubes and boiling tubes and some other glassware. What we have here is a test tube. As you can see, test tube is a small glass tube that can hold a small amount of solid or a liquid. Test tubes are usually used in the lab to conduct experiments in the small scale, when you want to observe how different chemicals react, when you very clearly want to make some qualitative observations, you will be using test tubes. We can take a small amount of reagents or 2 reagents together and observe how these 2 reagents react, sometimes while undergoing a color change or while producing a precipitate. So all of these different observations that take place when a chemical reaction is happening is easily observable when you conduct those experiments in a test tube. Apart from that, test tubes can be used to gently heat reaction mixtures as well. But keep in mind, students, you should not be subjecting the test tube to high heat. You should only be providing the test tube with a small amount of gentle heat or small amount of heat so that it does not crack under extreme heat. When it comes to talking about the test tube, it is not going to be able to stand on its own on your workbench. So therefore, after the use of a test tube or before the use of a test tube, you will see that we place the test tubes in a test tube holder or a test tube rack that we have here. Usually, you will have these types of test tube racks in your lab. Some racks can hold more than 7. This particular test tube rack can hold all the way up to 7 test tubes. When you are not using the test tube, your test tube should be in your test tube rack. So now, let's move on to a small practical and observe how we actually use the test tube. For that, we are going to be using copper sulfate. Now, before moving on to adding the copper sulfate into the test tube, let's observe how this copper sulfate solution is stored. This copper sulfate solution is stored in a stoppered reagent bottle. And why do we call it a stoppered reagent bottle? Because this has a stopper. This reagent bottle is made of glass and it is containing the aqueous copper sulfate solution, and it is closed off, or this container, as this container has a stopper, none of the reagent is going to evaporate and leave the container because the stopper provides an airtight seal. And due to this stopper being there, external contaminants will not come into contact with this reagent. Therefore, stoppered reagent bottles are a great way of storing different types of reagents, and when it comes to transporting different reagents as well, we will be using these stoppered reagent bottles. Apart from it preventing any evaporation or preventing any external contaminants coming into contact with the reagent, stoppered reagent bottles will also prevent accidental spills as well. If you accidentally tip this bottle over, you will observe there won't be any spilling happening because the stoppered reagent bottle will provide an airtight seal, or due to the stopper that we have over here, the reagent bottle will have an airtight seal now, which will prevent any liquid or any solution from getting spilled. So therefore, students, these reagent bottles are used for storing different types of chemical reagents, as well as it is used when it comes to transporting different reagents as well. As a precautionary measure, you should always label what is contained in these reagent bottles, otherwise you might not be able to use the contents in it without knowing what it contains. Apart from these clear reagent bottles, we sometimes have these tinted or amber or brown color reagent bottles as well. In these brown color reagent bottles, we usually store different reagents or chemicals that are sensitive to light. Certain chemicals or certain compounds can undergo decomposition, or certain compounds can change their composition when exposed to light. So to prevent altering the composition of different chemical compounds that are sensitive to light, we store them in these brown color bottles. When we store them in these brown bottles, it is safeguarded against the visible light or different light sources that are around it. So therefore, the reagent will not directly come into contact with this light, and because it doesn't come into contact with light, it will not undergo any change or it will not alter its composition. So therefore, when you store light sensitive or photosensitive reagents in these brown color bottles, we can ensure that their composition is unchanged. Now, after discussing why we use these brown color reagent bottles, we can move on to transferring a small amount of copper sulfate into our test tube. We can remove the stopper of the copper sulfate bottle that we have over here, and then we can transfer a small amount of copper sulfate onto our test tube. Now, when we take a small volume of our copper sulfate solution into one of our test tubes that we have over here, we can very clearly observe the color of this particular solution. Before taking the solution into our test tube, when it was present in our reagent bottle, sometimes we are not going to be able to very clearly observe the color due to thickness of the wall of the reagent bottle. But as you can see over here, we can very clearly observe the color of the copper sulfate solution we have now taken into this test tube. As you know, test tubes can be used in small scale reactions, as well as it can be used to carry out small dilutions and then observe different reactions when we mix two different reagents together as well. So let's carry out a small dilution. Over here we have concentrated sodium hydroxide, and over here we have a dropper. Now, before we carry out a small dilution, let's talk a little bit about this dropper. This dropper is made of plastic, and we often use these disposable droppers when carrying different reactions in the lab. These droppers are capable of dispensing small volumes of different reagents. The top part of the dropper is a small plastic bulb. You can squeeze this area to remove the air in the dropper, and if you insert the dropper in certain liquid or aqueous solution and release the bulb, you will see, due to the suction that is created, certain amount of liquid will come up to the dropper, and you can transfer that amount of liquid into a test tube, a beaker, or your reaction mixture. Usually, students, when you are handling a dropper, you are not supposed to place it flat on the workbench or on the table. If you leave it like that, the tip of the dropper might come into contact with the table, and if the table contains any contaminants, the tip will also be contaminated. Afterwards, when you insert the dropper into your aqueous solution to withdraw a certain amount of the solution, you will contaminate the entire amount that you have in the reagent bottle or in the beaker of that particular aqueous solution. So therefore, students, we normally don't place the droppers flat on the table. We can place it in a clean beaker like so. And when you are going to be using the dropper, it is always a good practice to dispense a small volume of your solution into a small beaker like I'm doing right now. After taking a small volume of this solution into this beaker, we can now use the dropper to draw a small volume of this solution into the dropper. Now students, what we have taken is concentrated sodium hydroxide, and we are going to observe how sodium hydroxide reacts with copper sulfate. But we want to use dilute sodium hydroxide to observe the formation of copper hydroxide pale blue color precipitate. So therefore, we are going to dilute this sodium hydroxide solution with the use of another test tube. We can transfer a very small amount of sodium hydroxide into our test tube here, and now we are going to add small amount of water with the help of a wash bottle. So as you can see, when I add water, we are diluting the sodium hydroxide solution. After adding water and diluting this concentrated sodium hydroxide solution, we produce a dilute solution of sodium hydroxide. So what we have over here is a dilute solution of sodium hydroxide. And now we can take our copper sulfate solution and add small amount of our dilute sodium hydroxide solution into our copper sulfate solution. You can see as we add our sodium hydroxide, copper sulfate is starting to produce this white color precipitate. Copper sulfate is starting to form this blue color precipitate. It's a pale blue color precipitate, copper hydroxide. We'll add a bit more sodium hydroxide. Now you can very clearly see the pale blue color precipitate that is getting formed as I add sodium hydroxide to this. Now students, this is copper hydroxide pale blue color precipitate that was formed when we added dilute sodium hydroxide to copper hydroxide. So students, this kind of changes that take place when a reaction is carried out is easily observed when we are using test tubes. And that is one of the reasons why we use test tubes to carry out these types of reactions. We will use minimum amount of reagents, as well as we can make very clear observations when mixing two different reagents together. I hope that is clear to everyone. Now we can move on to boiling tubes. Now students, what we have here is a boiling tube, and we are going to learn how to use a boiling tube correctly. Now boiling tubes are larger than test tubes. As you can see here, a small comparison between test tubes and boiling tubes. Boiling tubes have a wider opening and is usually used to carry out chemical reactions in somewhat of a larger scale compared to test tubes. And boiling tubes are made of borosilicate glass, and they are more resistant to high heat. So when it comes to boiling different types of aqueous solutions, or when it comes to heating different reaction mixtures to higher temperatures, we are going to be using boiling tubes. Since sometimes boiling may occur when you are heating reaction mixtures to higher temperatures, we call these glass tubes boiling tubes, because these are the tubes we will be using to carry out such reactions. So you might see an inscription here. You might see an inscription here that reads borosilicate. This indicates that this particular boiling tube is going to be able to withstand higher temperatures because of the fact that this is made of borosilicate. And to carry out this experiment, we will be using a small amount of lead nitrate, and what we have here is lead nitrate solid. We are going to dissolve the lead nitrate solid and form a small lead nitrate solution. We have our lead nitrate solid stored in this plastic bottle, and this plastic container is made with a resistant material that will not reactivate the solid compounds that it contains. Usually these plastic bottles that store solids usually comes with another small plastic lid that seals off the bottle or provides an airtight seal so that the contents inside the bottle does not come into contact with any external contaminants. And to take a small amount of the solid, we can use a metal spatula. So we have a metal spatula here. We will be using this metal spatula to transfer a small amount of this solid into a boiling tube. So when you are transferring the small amount of solid into the boiling tube, you can insert the metal spatula as far as you can insert it, and then you will transfer the solid into the boiling tube like so. Now we have taken a small amount of lead nitrate into our boiling tube, and after taking this lead nitrate into our boiling tube, we are going to place it on a boiling tube holder here or boiling tube rack here, and we are going to move on to closing this bottle containing our lead nitrate. And after that, with the help of a wash bottle, we are going to be adding a small amount of water into this boiling tube. So wash bottle is an lab equipment we use all the time. Wash bottles are usually containing distilled water. Sometimes if you want to dispense other solvents very carefully, you can use wash bottles as well. But please keep in mind, if you use any other solvent or any other reagent in a wash bottle, please make sure to label them so that you do not mistake them for distilled water. But for majority of the time, we use wash bottles to dispense distilled water. And this wash bottle usually has a squeezable body, meaning the body of the wash bottle can be squeezed, and as you gently squeeze it, the water from inside the wash bottle will be brought outside with the use of this plastic tubing you see here, so that we can direct the water stream directly into our reaction mixture. Or sometimes we use the wash bottle to rinse glassware, so we can direct the nozzle into the internal walls of the glassware to rinse the glassware thoroughly. And when it comes to the use of the wash bottle, it is quite important when controlling the addition of water into a reaction mixture, or when controlling the addition of water into a solid to dissolve the solid. So this gives us a good amount of control when it comes to adding water to different reaction mixtures, test tubes, or boiling tubes. So we are going to be adding a small amount of water into this boiling tube. You can see when I am using this, I have a lot of control over how much water I'm adding. I can squeeze it and then stop at my will and regulate the amount of water that I add to this boiling tube. And after adding a small amount of water, we can swirl the boiling tube around to dissolve the solid we have over here. So as we dissolve, we produce our lead nitrate solution. Now students, we have dissolved the lead nitrate we have taken over here, and since we took a considerable mass of lead nitrate, the solution that is formed here is quite high in its concentration. So we have a really high concentrated lead nitrate solution over here. We are going to transfer a small volume of this lead nitrate solution into a boiling tube, and we are going to dilute it by adding small volume of water. So now what we have here is a diluted solution of lead nitrate. And to this lead nitrate solution, we can add potassium iodide. And you're going to observe a precipitation reaction that is going to take place here. So we have potassium iodide here, and we are going to use a beaker and a small dropper to add potassium iodide into our lead nitrate solution. So let's take a small volume of potassium iodide into our beaker, and using a dropper, we are going to be taking a small volume of potassium iodide into our dropper, and we will be adding potassium iodide very slowly into our lead nitrate solution. Observe what happens when we add potassium iodide into lead nitrate. You can very clearly observe the formation of a yellow color precipitate here. Now we can see the formed yellow color precipitate very clearly. The more we add potassium iodide, more of the precipitate will be formed. The precipitate formed here is lead iodide. We have lead nitrate mixing with potassium iodide to produce lead iodide. The lead iodide, which is a yellow color precipitate that is formed, is dispersed throughout the aqueous medium, producing this yellow color suspension. This is not a yellow color solution. This is a yellow color suspension due to the yellow color lead iodide being dispersed throughout the aqueous medium. We are going to set it aside for the time being, and in the next part of our experiment, we are going to be heating this yellow color suspension. And as you know, lead iodide is insoluble in cold water, but when you heat it, what happens is this insoluble lead iodide precipitate starts to dissolve in water. So we are going to now show you how to use a Bunsen burner and how to use a boiling tube and heat a reaction mixture. And in this particular reaction, as you heat the reaction mixture, you are going to observe the color change from yellow to colorless. The yellow color lead iodide precipitate that is dispersed throughout the aqueous medium is going to dissolve more and more in water, and you're going to observe the formation of a clear solution. So let's move on to that observation. Now, students, we are going to learn how to use the Bunsen burner. Before we use a Bunsen burner, let's identify the parts of a Bunsen burner. We will have a metal barrel of the Bunsen burner here, and metal barrel is connected to the base of the Bunsen burner. And between the base of the Bunsen burner and the metal barrel here, you will have another arm that is connected to a gas tube which provides gas to this Bunsen burner. Apart from that, there is a small opening on the barrel that we have over here. So this small opening allows air to be taken in when the Bunsen burner is operating, and the collar right below the air hole allows us to control the amount of air that is taken into our Bunsen burner. So this collar is movable. We can move the collar up and down, and we can either completely close the air hole like so, or we can keep it partially opened like this, or we can completely keep it open like so. Now, we can use this collar to regulate the amount of air that is taken in to the Bunsen burner. So therefore, the type of flame that is produced here is going to change based on how we have closed the air hole, or closed based on how we have placed the collar on the air hole. First of all, students, before we light up our Bunsen burner, we'll close this air hole, and then after making sure that our collar is closed all the way up, we can turn on the gas supply and we can light the Bunsen burner. You can see, students, as soon as you turn on the gas supply and light the Bunsen burner, the flame that is produced is having this luminous yellow flame. And if you open this air hole very slowly, you can see this luminous yellow region of the flame decreases. As more and more air is taken into the Bunsen burner, more and more complete combustion will take place. So therefore, this luminous yellow color region will decrease as I open this air hole. You can see when I have partially opened it, the luminous yellow region of the flame decreased. So if I again close it back up, you will see the luminous yellow region again increases. Almost all of the flame is now a luminous yellow color, but as I open up the air hole, you will very clearly observe that the luminous yellow region of the flame decreases. When you have opened it halfway through, you are going to observe a blue color flame in the bottom region of the flame and a luminous purple color flame on the top area of the flame. This is the flame that is produced when you have opened the hole halfway through. You can observe this type of flame. And this type of flame, you can see there is a blue color middle region, and the top part and the surrounding region is a luminous violet color. This flame is good when it comes to heating up aqueous solutions with the use of a boiling tube. If you want to obtain another flame that has a more efficient burning of the gas that we provide to this Bunsen burner, we can open up this air hole a bit further so that you only observe a blue color flame without any luminous purple color region above it. When you open the air hole completely, you can see we produce complete combustion where the flame that is produced here has a blue color, and we would not observe the luminous purple color we observed earlier. So this provides the maximum amount of heat that can be produced with the use of a Bunsen burner, and you can use this when you want to provide a considerable amount of heat to a reaction mixture, or when you are heating different types of substances with the use of a crucible. You can provide this flame to the crucible to heat the substances to a higher temperature. Usually students, when we are trying to boil something with the use of a boiling tube, we will close the Bunsen burner air hole halfway through to obtain this type of flame where we have a luminous violet region to the flame as well. This type of flame is more suitable when it comes to boiling liquids that are contained in a boiling tube. So now we have the Bunsen burner set up. Are we going to heat this solution just by holding it with our fingers like this? Or do we have to take necessary precautions when heating a boiling tube with the use of a Bunsen burner? The answer would be we have to take necessary precautions. When you are heating the boiling tube will heat up as well as the contents in it. So if you are holding the boiling tube with your fingers or with your hand is also going to feel that high temperature. So to avoid incurring any burns to your hand, we can use a test tube holder. So we will be using this particular test tube and the boiling tube holder to hold our boiling tube. We can place the test tube or the boiling tube. For example, if you take a test tube, you can place it over here in the notched area of this metal clamp that we have over here. And then there's a movable metal piece that will bring these two metal pieces together and will allow this particular holder to hold on to whatever the glassware we place in between these two metal pieces. So the test tube or the boiling tube holder is an equipment that we usually use to hold on to test tubes or boiling tubes while heating these test tubes or boiling tubes. Whenever you want to release the test tube or the boiling tube, you can push back this movable metal piece and release the glassware. So this particular metal piece is movable, and as it moves, you can see the two arms that are found on the test tube holder come closer together, and it allows the secure holding of the test tube or the boiling tube. In this experiment, we are going to hold our potassium iodide suspension like so, and you can see it has a yellow color precipitate here. This yellow color precipitate is produced as such fine particles. It is dispersed through the aqueous medium to produce an appearance like this is an aqueous solution. You can see over here there's a yellow color precipitate produced, and this yellow color lead iodide that we produced earlier was produced as really fine particles or very fine solid particles, and since it was not soluble in cold water, we observed that it was present as a precipitate. However, when I heat this suspension, you will observe that this yellow color precipitate is starting to dissolve in hot water. So let's go ahead and heat this suspension. When you are heating a suspension or any liquid using a Bunsen burner, please make sure to bring it in and out of the Bunsen burner, and you have to make sure to point the opening of the boiling tube away from you and away from others in front of you as well. Away from you doesn't mean you have to point it at the person in front of you. Keep that in mind. So when you are heating this suspension, you can see the solid precipitate dissolved upon heating to produce a clear solution. So lead iodide is not soluble in cold water, but when you heat it, it dissolves in hot water. And you can see now it has produced a clear solution again. If you allow it to stand in room temperature for a while, you can again observe the formation of a yellow color precipitate. So when you are heating any aqueous solution or any liquid with the use of a boiling tube, you have to make sure to hold the boiling tube with the use of a test tube holder or a boiling tube holder, and you will normally slant the boiling tube. You will not heat it while keeping it upright like so. You will make sure that the boiling tube is at an angle. You will heat the area where there is the aqueous solution or the liquid present, and as you heat this boiling tube, you have to make sure to have a circular motion around the Bunsen flame so that the entire area that contains this liquid gets heated evenly. If you just hold it in one place, only one specific place will be heated mainly, and it could cause that area to overheat, and it could even result in cracks of the boiling tube. So to avoid those kind of accidents happening, we will normally heat the solution like so. You will heat the boiling tube while moving the boiling tube in a circular path like so. And if you feel like the solution is boiling like it is doing right now, you will move the boiling tube out of the Bunsen flame, and once it has cooled down, you can bring it back into the Bunsen flame once more. When it is boiling like this, you are supposed to move it away from the Bunsen flame. So students, that is how you would be using a Bunsen burner to heat or boil certain different liquids or solutions with the use of a Bunsen flame and a boiling tube. So when you are carrying out experiments in the lab, please make sure to follow these steps to safely conduct these experiments. So what did we learn about boiling tubes? Boiling tubes can be used to carry out experiments in somewhat of a larger scale compared to test tubes. Boiling tubes can be used to heat small volumes of different aqueous or liquid samples. Apart from that, you can use the boiling tube to heat solid samples as well. Boiling tubes can withstand higher temperatures compared to test tubes. And when you are heating a boiling tube or a test tube, you need to use a test tube or a boiling tube holder. And students, right after heating a boiling tube or a test tube under direct flame, don't subject it to lower temperatures straight away. The extreme temperature difference might cause the boiling tube to fracture, and therefore you will not be able to use this glassware again. So students, extreme temperature changes is not good for glassware. So after heating any glassware under direct flame, you are not supposed to immediately cool it. So you will allow it to gradually cool down in air. Do not ever place it in a cold water bath or cold ice bath right after directly heating a boiling tube. After subjecting a boiling tube to direct heat, you are not supposed to immediately cool it down. So keep that in mind, students. Before handling it, make sure that it's sufficiently cold. So after it has sufficiently cooled down, then you can proceed to handling it with your hands once again. So you are not supposed to touch it right after heating it under direct flame. Of course, that will result in a burn. So therefore, after heating it under direct flame, you are supposed to allow it to stand for a few minutes, and once it has cooled down to room temperature, temperature to which you can handle the boiling tube, you can proceed to remove the boiling tube holder and handle it with your hands. So students, we observed earlier in the reaction we produced lead iodide, which was a yellow color precipitate, but upon heating, all of the lead iodide dissolved to form a clear solution. When this solution cools down to room temperature, you will see the formation of water insoluble lead iodide precipitate once more. So you can see the formation of a yellow color precipitate once more as this solution cools down. That summarizes the use of test tubes and boiling tubes. While we were looking at test tubes and boiling tubes, we learned about the use of the Bunsen burner and how to handle a Bunsen burner. We learned about reagent bottles, especially we learned about stoppered reagent bottles. We learned about droppers and wash bottles, and how to use a spatula to transfer solid samples onto test tubes, boiling tubes, or your reagent mixtures. So after discussing this point, we are going to now move on to our next set of glassware. Now students, we are going to be looking at beakers. So in the lab, one of the most important glassware that you're going to come across is beakers, because we will be using them quite often. Now, beakers can be used to hold certain amount of liquid or different types of solutions, transfer liquid or solutions from one container to another, sometimes even to carry out a heating of different types of reaction mixtures. We can use beakers. We often conduct reactions in beakers if we have to use large volumes of reactants to carry out a reaction. Instead of using a test tube or a boiling tube, we will be using beakers. Beakers come in a variety of different sizes. We have beakers that can hold around 50 milliliters, all the way up to, we have over here 1 liter beaker, but there are larger beakers than this as well that can hold about 2 liters, 3 liters. There are larger beakers which can hold larger volumes of water or different types of solutions. Now, these beakers are going to be used based on the reaction you are carrying out. If you are carrying out a reaction where you are going to only use small volumes of different reactants, then you can use a beaker that has a smaller capacity. If you are going to carry out a reaction where you will be using large volumes of different reactants, then you have to choose a beaker that will suit your need at the time. Apart from carrying out reactions, as I mentioned earlier, you will also be using beakers to gently heat different reaction mixtures. So we will be using a beaker to gently heat reaction mixtures as well, with the use of a proper heat source such as a Bunsen burner, or sometimes you can use a hot plate as well as your heat source. Apart from using beakers to carry out reactions, and heat reaction mixtures gently. You can also use these different sized beakers to prepare water bath by placing the beaker on a setup that we have over here. I will explain this setup in a second. So you can use beakers to set up water baths, and by placing cold water in a beaker, we can prepare cold water baths, or sometimes by placing ice or crushed ice in a beaker, we can prepare ice baths. So beakers are versatile glassware that we find in the lab, which we will be using all the time. So you should be uh, having a good enough understanding about what we use beakers for and how to use these beakers based on their size and their make. Certain beakers will have these inscriptions saying borosilicate. So this indicates that this particular beaker is made of borosilicate, which can stand high temperatures. But certain beakers will not have this written inscription, which might indicate that those beakers are not very suitable for heating. So when you're trying to heat a beaker, always look for your borosilicate inscription on the beaker, which will communicate the fact that these beakers can be used for heating. Now students, let's take a look at how we can prepare a hot water bath with the use of a beaker. So we have here a beaker that can measure all the way up to 250 milliliters, and we have some graduation lines here as well. One of the most important things to know about beakers is that these graduation lines are imprecise, meaning you should not be using these graduation lines to measure volumes of liquid accurately. Beakers are not volumetric glassware where all of these volumes are going to be very accurate. So therefore students, these graduation lines that you see over here at 50, 100, 150, 200, 250 are not very accurate. So therefore, if you are planning on measuring, let's say 250 milliliters of water, if you use a beaker for that, you have to understand you have not measured 250 milliliters very accurately. This is merely a rough measurement and it is not going to be very accurate. So therefore, you do not use beakers to measure different volumes. Instead, this is there for a rough measurement, for you to have a rough idea about the amount of liquid that is present in the beaker. You will not use the beaker as a volumetric equipment or volumetric glassware, because these measurements are imprecise. They are not going to be very accurate if you use a beaker to measure certain amount of volume. So while keeping that in mind, we can now proceed to prepare our water bath. When you are going to prepare a water bath, you will need a Bunsen burner. So we will light our Bunsen burner, and then we will be placing this tripod. A tripod is an equipment or a device that we will be using to hold different types of glassware that has a flat bottom. And on top of the tripod, we will be placing our wire mesh, or we'll say gauze woven wire mesh. So in the middle of the wire mesh, you will see a small area where there is a gauze woven area that is there to make sure that the heat that is provided from the Bunsen flame is distributed across this area evenly. Otherwise, when you turn on the Bunsen flame, the heat that is provided will only be directed at one specific location of the beaker. So at that point, one specific location of this particular glassware might overheat, and this could lead to that area expanding and results in a cracking or a breaking of the beaker. So to avoid this from happening, we use this gauze woven wire mesh that will disperse that heat, and it will produce an area where the heat is evenly distributed. So when these kind of flat bottomed glassware is placed on these types of wire meshes, you will observe that the beaker is not going to be heated only in one location, but due to the wire mesh that we place over here, it will distribute the heat, and the entire bottom region of the glassware is going to receive an uniform amount of heat. So students, that is the purpose of this wire gauze, or we call it a wire mesh as well. We will be using wire mesh and a beaker to set up our water bath. So let's move on to that setup now. Now students, we have turned on the Bunsen burner and we have a beaker filled with water here, and as we heat the beaker, the water in the beaker will also heat up, and when the water heats up, we can use this setup as a water bath. So the reason for using a water bath is when you are conducting certain experiments, we need to provide a more controlled amount of heat to reaction mixtures. There are certain reaction mixtures which require a more controlled heating, and that can be provided with a water bath. So that is why we use a water bath. Apart from that, when you are heating organic solvents that are usually flammable, you will never heat them using a direct flame. You will never heat organic solvents with a boiling tube or a test tube, and you will not directly heat the contents in the boiling tube or the test tube using a Bunsen burner. So if you want to heat any organic solvent that you have taken into a boiling tube or a test tube, you can heat them gently with the use of a water bath, where you have more control over the heating. So don't directly heat any organic solvents that you may have taken to a boiling tube or a test tube directly over the Bunsen flame. Instead, you can take the contents into a boiling tube and then heat it with the use of a water bath that you have prepared. So to demonstrate the use of this type of water bath, we will now carry out a small reaction. Over here in a reagent bottle, we have ethanol. Ethanol is an aldehyde, an organic substance. So if you are carrying out a reaction with ethanol, and if you want to heat the reaction mixture, you will not directly heat the reaction mixture. Instead, you will use a water bath. And we have Benedict solution here. And when you mix these two reagents together, you will see that the reaction mixture is going to appear blue. However, upon heating this, when you provide heat, the reaction that takes place between these two reactants will happen faster and will result in the formation of a brick red precipitate. So students, this is one of the ways in which you can identify aldehydes from ketones, and this particular aldehyde is ethanol. We can take a small volume of ethanol onto a boiling tube. You can see it is colorless, and then We can add small volume of Benedict's solution into ethanol. Now students, you can observe after mixing the two reactants together, the reaction mixture is blue in color. This is due to the presence of copper 2 plus ions in the medium. When you have copper 2 plus ions in this aqueous medium, the aqueous medium appears blue in color. However, if you place this reaction mixture in a water bath and allow it to heat up for a while, you will observe this color changing from blue to green and then to yellow and finally to a brick red color. Now this brick red color will be there due to the forming of cuprous oxide or Cu2O precipitate. However, our main observation here should be how we heat this reaction mixture. This reaction mixture is only going to be heated with the use of a water bath. You are not supposed to heat it using a direct flame, so you will be heating this reaction mixture using a water bath. And you can see after placing it in the water bath for a while, little by little, the color changes to a green color. Earlier on, it was blue. Now it is green. You can see the top bits of this reaction mixture now appears to be a bit yellow. But if you allow this reaction to take place a bit further, you can see the color further changes and produces a brick red color. Right now, majority of the solution is somewhat of a yellowish green color. We will let it heat for a little while longer and you can observe the formation of the brick red color when you heat it using a water bath. And as I mentioned earlier, students, when you are heating any liquid or aqueous solution or reaction mixture with the use of a boiling tube, you are not supposed to point the opening of the boiling tube or the test tube towards you. And you should never point it away from you towards another person as well. So if you are pointing it away from you, please make sure that there is no one in front of the opening of the boiling tube or the test tube. If any splashing is to occur, you need to make sure that it will not go and harm another person or yourself. So therefore, students, when you point this opening of the boiling tube, please make sure not to point it at yourself or at anyone else. You have to point it away from yourself and others as well. Now this boiling tube is becoming a little bit hot, so you should not be handling it with your hands. So we can use a boiling tube holder to hold it like so. You can observe now it has changed color to a bit of a brick red color. We can let it sit there for a while until it completely changes color. Now students, the reaction has gone to completion. We can now observe the precipitate formed here. You can see the reaction mixture when we initially started was blue in color and it was a solution, but what we have formed here is a brick red color precipitate. So the copper 2 plus aqueous ions in the medium in the initial reaction mixture cause the blue color of the solution, but after the reaction has gone to completion, copper 2 plus has now turned into Cu2O, cuprous oxide, and that is why you observe this brick red color. So the precipitate particles are dispersed in aqueous medium. That is why the entire aqueous medium appears brick red. But keep in mind, students, this is not a solution. This is a suspension where fine solid particles are dispersed through the aqueous medium. Now, we will allow it to stand in air for a while, and then we can place it in our boiling tube rack that we have over here. You should not be handling it when it is really hot. After taking it out of the water bath in a few minutes, or sometimes within the span of a minute or two, it will cool down, so you can actually handle it with your hands. So by now it has cooled down to the point where we can handle it with our hands. So after it has cooled down, we can place it in our boiling tube rack. Now students, that is how we will use a beaker to set up a water bath. Now, a few things to keep in mind is that if you run out of water in the water bath due to water evaporating, you have to remove the heat source and make sure that the water actually never runs out of the water bath. If all of the water evaporates, when the beaker is heated without any water in it, there is a chance of beaker overheating and it may crack due to the amount of high heat that it receives. Apart from that, do not heat the beaker without a wire mesh. At that point, only a specific part of the beaker will be heated, or it will have really high amount of heat provided to a specific region of the beaker without evenly distributing the heat. So therefore, at that point, beaker again might undergo extreme stresses, and it could cause the beaker to crack, which can result in accidental spillings of hot water, which could be dangerous. So therefore, students, if you follow these steps, when you are setting up your water bath, you can safely conduct experiments where the use of a water bath is needed. So students, now we can move on to observe another use of beakers. Let's move on to another experiment. Now students, we are going to observe how we are going to be using different beakers when transferring liquids from one beaker to the other, and we are going to use a beaker to prepare a solution as well. And we know we do chemical reactions in beakers as well. So when it comes to carrying out reactions in different beakers, we sometimes have to pour one reactant from one beaker to another, and we are going to observe how that is safely done. So over here we have a bit of a large beaker, and we have a smaller beaker here with water. Now imagine pouring the contents of the smaller beaker into the larger beaker, and see what happens if you don't use the correct practices. So observe what happens to the walls of this larger beaker. Did you observe, as I was pouring the liquid into this larger beaker, a lot of water got spluttered, or water splashed all over this interior walls of the beaker. Since this beaker is large enough, none of the water actually splashed out of this beaker. But if you have this type of a transferring method, when it comes to transferring different volumes of liquids from one beaker to the other, if you transfer like I transfer the liquid in the previous instance, some of the liquid will actually splash out of the beaker. Since I used a large beaker, you can see it didn't splash all the way out of the beaker, but you can very clearly see that some splashing has occurred because the interior walls of the beaker is now fully covered in water droplets. So this is not the correct way to transfer liquids from one beaker to the other. Instead, if you want to pour the liquid quite fast, now if you are pouring liquids very slowly, you can do that by pouring it along the walls of another beaker. But a more precise way of pouring the liquid from one beaker to the other would be to use a glass rod, or also known as a stirring rod. We use these types of rods to stir solutions as well. As glass is an inert material, we can use glass rods to stir solutions like this. However, when transferring solutions as well, we can use a glass rod. Now, with the help of a glass rod, we can direct the liquid flow to an area where you want the liquid flow to be at. So in this case, since we want the liquid to fall down in the center of the beaker, we will place the glass rod in the middle of the beaker like so. Take precaution not to push the glass rod very strongly down on the beaker. If you push it too hard, the bottom of the beaker might get cracked. So just gently place the glass rod on the beaker, and then you can start pouring your liquid onto your glass rod. If you want to transfer all of your liquid quite fast, you can do so with ease if you are using this method. If you transfer your liquid quite fast without using this method, definitely there will be some splashing occurring, and this may result in some of your solution or some of your reaction mixture splashing out of the beaker, which could result in errors as well as waste, and it could also be problematic if the reaction mixture contained any harmful substances. It can be harmful to you and to others around you if you allow the liquid to splash all over the place when you transfer the liquid from one beaker to the other. So, do you see any water droplets around this beaker? Do you see any water droplets around this beaker? The answer to that would be no, because we used the glass rod to direct the flow of water and make sure that it is not getting splashed all over the place with the use of this glass rod. So if you want to quickly transfer volume of liquid from one beaker to the other without the liquid splashing all over the other beaker, you have to use a glass rod. Or if you are slowly transferring the liquid from one beaker to the other, you can do so by pouring the liquid like this along the wall of the other beaker. So at that point, again, you will not have any splashing occurring because you will be transferring the liquid along the wall of the other beaker. So that is how you can transfer liquids from one beaker to the other. And after observing that, we are now going to move on to preparing a solution of calcium hydroxide. Now students, we have calcium hydroxide here. You can see this solid calcium hydroxide contained in this white color plastic bottle. We have now opened the calcium hydroxide bottle, and there is another plastic cap providing an airtight seal to our calcium hydroxide solid that we have over here. And using a spatula, we are going to transfer a small amount of calcium hydroxide to our beaker here. Now, we do not usually need this much calcium hydroxide to produce a calcium hydroxide solution, as calcium hydroxide is not very soluble in water. However, after this process, we are going to be carrying out a filtration. So, to observe the filtration process very clearly, we will be using somewhat of a significant amount of calcium hydroxide solid. So, we have our calcium hydroxide taken into this beaker. We can now proceed to close this calcium hydroxide solid containing bottle here. And then we can proceed to add water. We can add water with the use of a wash bottle. So we can see there are some water droplets here on the wall. If you want to remove them, you can use the tip of the wash bottle to direct a stream of water towards those areas where you need to wash the container. Now, after filling this beaker with distilled water, we can proceed to mix it with the use of a glass rod. So we can now stir this solution with the use of a glass rod. So students, as you can see here, most of the calcium hydroxide we added to this beaker have not dissolved, as calcium hydroxide is not very soluble in water. However, some of the calcium hydroxide has dissolved in this aqueous medium, and we need to obtain an aqueous solution of calcium hydroxide. But what we have over here is a mixture of the calcium hydroxide solid dissolved or suspended in a calcium hydroxide aqueous solution. So I repeat, what we have over here is our calcium hydroxide aqueous solution mixed with the calcium hydroxide solid that was not dissolved in the aqueous medium. Since only a small portion of the calcium hydroxide got dissolved in water, majority of the calcium hydroxide solid is still present in this reaction mixture. So therefore, students, to obtain a calcium hydroxide aqueous solution without any solid particles in it, we need to filter this. Filtration is usually done with the use of a funnel. We can use a funnel to carry out filtration along with the use of a filter paper. We are going to fold the filter paper in an appropriate manner, and then we are going to place this folded filter paper in our funnel over here, and after that we will be pouring these contents of this beaker onto our filter paper. These filter papers usually have different gradings. the higher the grading, the finer the particles that they can filter. Usually, over here, the filter paper that we have is capable of filtering these calcium hydroxide solid particles that we have over here. Usually, students, there are two ways of folding this filter paper. One of the easiest ways is to fold the filter paper once, like this, and then you can fold it once more. And after folding it twice, like this, you can select one of the outer flaps and open it up like this. So when you have created an opening like this, you can place it inside the funnel like so, inside the funnel like so, and continue to pour the mixture or mixture containing the aqueous calcium hydroxide and solid calcium hydroxide onto this filter paper. That is one way of folding your filter paper. There is another way of folding the filter paper to indicate that we will be using another filter paper. You can fold the filter paper once, like we did in the previous instance, and then we will fold the filter paper few more times. Now we have folded twice, and now thrice, and finally, after folding it thrice, we will fold it one more time, like this. Then we can open it up. After opening it up, we have to manipulate this filter paper in such a manner where we can actually produce a fluted shape. We actually call this the fluted filter paper. We will fold the filter paper like so, and we will create this type of shape. This is referred to as the fluted method of folding the filter paper. So after folding it in this particular manner, we can now place this filter paper in our funnel like so. As you can see, students, this filter paper will not stay in place. If you want to make sure that the filter paper stays in place inside the funnel, you have to make it wet by applying certain amount of water or the solvent that you used to prepare your reaction mixture. In this case, we have an aqueous mixture where you have an aqueous calcium hydroxide solution mixed with solid calcium hydroxide. So this is present in aqueous medium. So therefore, before starting the reaction, you can make this particular filter paper wet with water. We will add water and make the filter paper wet with water, and then it will stay in place. However, you can't do this if the reaction mixture you have in front of you was prepared with the use of an organic solvent. If this is an organic solvent-based reaction mixture, then you should not be adding water to wet the filter paper. Instead, you have to use the organic solvent that you used to prepare this reaction mixture. So therefore, students, you have to be very clear. You have to wet the filter paper with the solvent that was used to produce this mixture. If the solvent is water, you can wet this filter paper with water. If the solvent is an organic solvent, then you have to use the same organic solvent to wet this filter paper. So if you follow these instructions, you will be able to very successfully able to filter a solid mixture and obtain the solid sample and the filter rate separately. So both of these folding methods are used when it comes to filtering solid liquid mixtures. And this fluted method provides more surface area, and therefore the filtration can happen faster than this simple folding method. Depending on your requirement, you can use either one. We will use this fluted folding method in this particular experiment, and we will place it now on our funnel like so. And you may have already observed that the funnel was sitting on a ring clamp. It's known as the ring clamp. This can be used to hold glassware such as the funnel or separatory funnels and so on. So you can use this ring clamp to hold the funnel, but keep in mind, when you are using a ring clamp, you have to first ensure the size of the ring is not too large or not too small. It should be just right to hold the funnel. If it is too large, it will go through and it will not hold the funnel. If it is too small, then the funnel will be unstable. So therefore it should be a ring clamp of the correct size when you're trying to hold the funnel in place with the use of a ring clamp. So now we will proceed to filter our calcium hydroxide. So to make sure that this particular filter paper stays in place, we can add water to the filter paper and make the filter paper wet. Now students, we have made the filter paper wet. We can now proceed to add our calcium hydroxide mixture to this filtering setup, and to direct the flow of this mixture we will be using a glass rod. So I will keep the glass rod suspended in air like so. Make sure not to touch the internal area of the filter paper. Filter paper is now soft because it is made wet with water. If you poke the filter paper, this glass rod will cause a tear in the filter paper and you will have to start over, because whenever there is a hole in the filter paper, the filtration will not happen properly. So therefore you will have to start over. So to avoid that, we will place the filter paper in mid-air like so, and we will start pouring our reaction mixture onto our filter paper using the glass rod. When you use this fluted method to fold the filter paper, the filtering happens a little bit faster than when we use the simple folding method, that I showed you first. So therefore, if you need to obtain a filter rate a bit faster, then you can use this fluted method to fold your filter paper. And students, if you start to see any solid particles in your filter rate, now what remains on the filter paper is the solid. From this solid liquid mixture, the solid will be retained on the filter paper, and only the liquid will come down into our small beaker that we have over here. And you can observe the difference between the mixture, calcium hydroxide mixture, and the filter rate that we have over here. It is very clear. That indicates that there is no tear or no holes in the filter paper, allowing any solid particles to come through the filter paper. So there is no need to change the filter paper here because the filter paper is still intact. Now we'll continue to pour our calcium hydroxide mixture here onto our filter paper, and we will allow it to get filtered. When you are adding your mixture to the filter paper, make sure to not pour the reaction mixture over the filter paper. As you can see, the filter paper is ending all the way up here. If you keep adding more and more reaction mixture, at one point the reaction mixture will overflow out of the filter paper, and that amount of liquid or that amount of mixture that is overflowed will directly come down into this beaker where we are collecting the filter rate. So again, if that ever happens, you will not obtain only aqueous solution sample here. There will be still some amount of solid coming into our aqueous sample here. So if that ever happens, you will have to carry out another filtration to make sure that all of the solid is removed from this aqueous solution. Now students, this is how a filtration is usually carried out. So we observed the uses of the beaker, and we have little bit more calcium hydroxide here. We will filter it out using glass rod once more. Now again, please do observe the difference between the filtrate and the mixture. Observe the difference between the filtrate and the mixture. Filtrate is very clear, and if you take a look at the mixture is cloudy due to the calcium hydroxide solid particles being suspended in that aqueous medium, creating a liquid solid mixture. So you can very clearly observe the difference between the mixture and the filtrate. We'll now transfer the last bits of this reaction mixture We have now transferred the last bits of the reaction mixture onto the filter paper. If there are still small amounts of solid residue on your beaker, you can add a small amount of water and transfer those into this particular filter paper as well, but that is an additional step. If you do not want to dilute this filtrate further, you do not have to do that. But if you want to obtain all of the solid that is found in this beaker, you have to wash the beaker and then transfer the washings into our filter paper, and the filter paper will filter the liquid from the solid, and solid will remain on the filter paper. You can take the filter paper out and you can dry it and obtain the solid from the filter paper. If you are more interested in the filter rate, you can, after the filtration is over, you can directly obtain the filter rate without any issue. But if the filter rate contains any solids in it, that means you have conducted this filtration incorrectly. That means either you have poured some of the mixture outside of the filter paper, or the filter paper might have had some tears in it when you were introducing the mixture. So some of the solid might have come into the filtrate. At that point, you will have to conduct this filtration one more time. In our filtrate, you can see there are no solids in it. So therefore, this filtration is a successful filtration. After the filtration, if you want to keep the filtrate stored in a different reagent bottle, you can take a reagent bottle, label what is going to be stored in this reagent bottle, and you can transfer the filtrate onto our reagent bottle. So let's move on to transferring this filtrate into our calcium hydroxide labeled reagent bottle. You can see the filtrate is very clear, indicating that there are no solids in the filtrate. You can't see any solid particles floating about as well. Again, this is a sign of a successful filtration. If any solid particles have made it their way into the filtrate, then you have to conduct another filtration to remove all the solid particles. Now students, we have prepared a calcium hydroxide aqueous solution, and we have stored it in a stoppered reagent bottle, and we have labeled it as well. So in this part of our experiment, we learned how to use beakers, different applications revolving around beakers, and we even learned how to use a funnel and filter paper for filtering liquid solid mixtures. So after learning all of this, we can now move on to the next setup. Now students, we are going to be looking at another equipment that we use quite often in the lab, that is conical flasks. Now conical flasks are used quite often when adding different reagents and mixing them together. We will use conical flasks. Conical flasks also can be used to store certain amount of liquids in them. Apart from that, you can carry out gentle heating of different reaction mixtures or different types of liquids with the use of our conical flask. And due to the narrow neck of the conical flask, we can close the conical flask with the help of a rubber stopper. So this is also very useful, especially when you are carrying out different reactions with volatile liquids, If you want to close it for a very short period of time, you can do that. But if you keep it closed for a long period of time, it could be risky, because as the gases evaporate, there will be some pressure built up here. So just for a very small period of time, if you want to keep it stoppered, you can do that. But this small opening also allows us to connect rubber stoppers that are connected to other lab equipment, like a thistle funnel here and a delivery tube here. So conical flasks are quite versatile glassware that is used for many purposes. One of the most important things to know about conical flasks is that due to these slanted walls that you have in the conical flasks, when you add different reagents or different chemicals into the conical flask, you can mix the contents in it by swirling it around without having the fear of the reaction mixture splashing out when you are swirling it around. You can't do the same with a beaker, as when you keep swirling the beaker around, if you move faster, the reaction mixture can spill out. But due to these slanted walls and the narrow neck of the conical flasks, you can swirl the contents in it around and mix it really well without the mixture splashing out of the container. Depending on the type of reaction that you're carrying out, based on whether the reaction is going to be using a large volume of different reactants or a small volume of different reactants, you will have to use different types of conical flasks. Over here we have two different conical flasks with two volumes. This conical flask has an overall volume of 100 milliliters, and the conical flask over here can hold up to 250 milliliters. So based on your requirement, you can have conical flasks with different volumes. So in this particular experiment we are going to conduct with the use of this conical flask, we are going to use the 250 milliliter volume conical flask, and we are going to see how we can use conical flasks to carry out reactions where they are producing gases. And these types of conical flasks are ideal for this because they can be stoppered due to the presence of a narrow neck here. And the gases produced will rise up and can be taken out of the conical flask with the use of a delivery tube. So over here we have a stopper, a rubber stopper connected to a thistle funnel, and the thistle funnel comes with a stopcock, or else it comes with a valve that will allow us to regulate the amount of the liquid in the thistle funnel that is dispensed per given unit time. So we can regulate the speed at which the liquid in the thistle funnel is released into the conical flask here. And another rubber tubing is connected to the stopper here. So this rubber tubing is connected through a glass tube to the rubber stopper, and we have a flexible rubber tubing here that will allow us to deliver this gas that is produced onto different reaction mixtures. So in this particular setup, we are going to have our rubber stopper placed on the conical flask like so, and we are going to take calcium carbonate into the conical flask, and we are going to slowly add HCl onto our calcium carbonate. This will produce carbon dioxide gas, and we can take carbon dioxide gas out of this setup with the use of this delivery tube. And the produced carbon dioxide gas is going to be sent through calcium hydroxide that we produced earlier. So the carbon dioxide gas is going to be sent through calcium hydroxide aqueous solution we produced earlier. Calcium hydroxide aqueous solution is also known as lime water. So you will see as carbon dioxide is sent through lime water turns milky when carbon dioxide is sent through lime water. Now, before we attach a rubber stopper to any glassware, you have to make sure that we apply a small amount of grease around the rubber stopper. Otherwise, once you tighten this rubber stopper onto glassware, when you're trying to remove it, due to the high amount of friction that is going to be there between the rubber stopper and the glassware surface, there might be certain damages introduced onto the glassware. So to make sure that the glassware doesn't break when you remove the rubber stopper from the glassware, we need to always apply a small amount of grease around the rubber stopper. We can gently place the rubber stopper like this on this setup, and we can move to adding small amount of grease on the rubber stopper. We have grease here. We will add a small amount of grease onto our rubber stopper like so. And we can now place it over here without any issue. We will still not tighten it, because when you tighten it, we will not tighten it just yet. If you tighten it now itself, we will not be able to add our calcium carbonate solid onto our conical flask if you tighten this rubber stopper onto the conical flask. So therefore, we will not tighten it just yet. We will move on to first adding the calcium carbonate over here, and then we will make sure we have the HCl added to this funnel as well, and then we will make sure that the rubber stopper is properly fixed onto our conical flask. Now we will take our calcium carbonate solid that we have over here. We will use a spatula to transfer a small amount of calcium carbonate into our conical flask. After taking a small amount of calcium carbonate into our conical flask, we can proceed to close this conical flask with the help of a rubber stopper. Now remember, the rubber stopper was applied with grease so that we can easily remove it when it is time for us to remove the rubber stopper. Now we have fixed it tightly in place, and then we will make sure that this thistle funnel has its stopcock in a closed position. So when the stopcock is closed, it will be in a horizontal position, and you can also see the opening of the valve over here, so we can be very sure that it is closed right now. After ensuring that it is closed, you can proceed to add HCl to our thistle funnel. So we have our HCl solution here. We can add a small amount of HCl into our thistle funnel. Now students, the reason why we use a thistle funnel for such a reaction is to make sure that we have control over the addition of HCl onto our calcium carbonate that we have in the conical flask. If you just add a small amount of HCl directly to it without controlling, there will be a lot of carbon dioxide gas produced all at once, and then we will not be able to observe a gradual release of carbon dioxide gas. So with the help of a thistle funnel, we can add HCl little by little or even faster depending on your requirement, and make sure that we have control over the addition of HCl. And then when HCl comes into contact with calcium carbonate, carbon dioxide gas is produced, and the produced carbon dioxide gas will not be able to exit the setup through the thistle funnel, because there will be certain volume of HCl still present in the thistle funnel. So therefore the thistle funnel is not going to be open to the atmosphere for carbon dioxide to pass through. However, over here we have the opening for the delivery tube. So the carbon dioxide gas that is produced will be able to enter the delivery tube, and through the delivery tube it will be directed to a reaction mixture. In this case, it will be directed to calcium hydroxide aqueous solution, and we are going to observe what type of reaction that takes place when carbon dioxide comes into contact with calcium hydroxide solution. So before we start this reaction, we will take a boiling tube and add a small amount of lime water or calcium hydroxide into our boiling tube here. And then we can use a test tube rack and place these delivery tubes or the tip of the delivery tube inside our lime water solution, and we can proceed to add HCl little by little onto our calcium carbonate solid that we have here. You can see when we add HCl little by little, you can see a gas is evolved from the tip of this delivery tube. You can see there is a gas that is introduced into our calcium hydroxide solution we have over here. If you want to increase the speed of this reaction, you can add a bit more HCl, and then you can see as more HCl comes into the setup, there will be carbon dioxide produced a bit faster. Now students, as you can see, when HCl comes into contact with this calcium carbonate solid, you can see carbon dioxide gas is released, and that released carbon dioxide gas enters this calcium hydroxide or lime water solution through the delivery tube. So if you add a bit more HCl, you can see When HCl comes into the medium, the reaction happens a bit faster, and you can observe little by little that the calcium hydroxide solution we had is turning to a milky color. Now, students, you can very clearly observe when we added HCl to calcium carbonate, carbon dioxide gas was produced, and we used this flexible tubing or a delivery tube to deliver that carbon dioxide gas that was produced inside this conical flask uh, to this particular boiling tube where lime water was present. So the carbon dioxide produced in the conical flask was delivered with the use of a delivery tube into this lime water, and when we initially started, the lime water was a clear solution, but as carbon dioxide passed through it, the lime water turned milky. In the presence of carbon dioxide, lime water forms calcium carbonate, which is water insoluble. So therefore, the calcium carbonate fine precipitate particles that are formed is going to be suspended through the aqueous medium, producing this milky appearance in lime water. So students, this is how we will be using a conical flask for a reaction where we produce gases. Conical flasks can also be used for gentle heating, and it can also be used for mixing reactants together, especially if you want to keep swirling the reaction mixture. You can very easily do that with the use of a conical flask. Due to the flat bottom the conical flask has, you can very easily place it on a table, and due to the shape of the conical flask, tipping of the conical flask is not going to be easy. So this particular lab equipment, due to its flat bottom and the shape of it, will not easily be tipped. So we will be using this type of lab equipment to mix reagents and store different types of reagents temporarily as well. So students, this is the way in which we can use a conical flask. Apart from using it for producing gases, we can also use it for mixing reagents as well. To indicate how mixing is easy with a conical flask, you can observe here when you swirl the contents inside the conical flask, it will not spill the contents in it. Due to these slanted walls it has, it will not easily spill any contents that are in it. So therefore, you can swirl it really well. Whatever the contents in it can be mixed really well through swirling without having the fear of any spilling out of the conical flask. And the narrow neck of the conical flask allows us to clamp it using a clamp when carrying out different experiments. So this narrow neck allows us to clamp these conical flasks as well, which is another use of conical flask. When it comes to beakers, we cannot clamp any beakers with the use of a clamp. However, when it comes to conical flasks, this is possible due to the narrow neck that is usually found on conical flasks. Now we looked at how we can use a conical flask. It is now time for us to move on to learn how to use a volumetric flask. Now students, we are going to be looking at volumetric flasks. While we talk about how to use volumetric flasks, we will also take a look at how to use pipettes and burettes as well. So now let's take a look at volumetric flasks. So volumetric flasks are a type of volumetric glassware. These volumetric flasks can measure liquids up to a specific volume very accurately. There's only one mark that is found on each volumetric flask, and when you fill a liquid all the way up to that mark, and when the bottom of that liquid's meniscus aligns with the mark that is found on our volumetric flask, we can say we have accurately measured the volume that is mentioned on the volumetric flask. The flask that I'm currently holding has a volume of 100 milliliters. If you fill a liquid all the way up to this calibration mark that you find over here, at that point, if the bottom of the meniscus of the liquids, if it aligns with this calibration mark, that indicates we have precisely taken 100 milliliters of that liquid into this volumetric flask. You cannot measure intermediary values using a 100 milliliter volumetric flask, meaning using 100 milliliter volumetric flask, you can't measure 75 milliliters or 50 milliliters or so on and so forth. Volumetric flasks come in few different sizes. The one that I'm holding here has a 100 milliliter volume, but there are smaller volumetric flasks as well. And in the middle here we have a volumetric flask that can measure 250 milliliters, and the one on my right hand side has a volume of 500 milliliters. Based on the reaction you are carrying out, based on what type of solution you are preparing, you will have to use volumetric flasks of different volumes. Based on the volume of the solution that you need to prepare, you will have to use different types of volumetric flasks. Some of the volumetric flasks that you can find in the lab are given here. Like I mentioned here, we have 100 milliliter volumetric flask, 250 and 500 milliliter volumetric flasks in front of us, but these are not the only volumes that you will find in volumetric flasks. There are other volumes smaller than 100 milliliters and larger than 500 milliliters as well. So what is the purpose of using a volumetric flask? Why do we use volumetric flasks? Volumetric flasks are used mainly to prepare standard solutions. When you are preparing a solution where the concentration is known, or when you are preparing a solution in the hopes of standardizing its concentration, you will be using a volumetric flask. Volumetric flasks are primarily used to prepare standard solutions. So when you are using a volumetric flask, you need to be aware of a few things. We'll keep some of the other volumetric flasks aside for the time being. We will take this volumetric flask. When you are handling a volumetric flask, it is important to note that you should not be handling the volumetric flask only by touching the narrow neck area of the volumetric flask. The narrow neck area could be somewhat prone to breaking, so therefore do not handle the volumetric flask only by touching from the neck of the volumetric flask. And when you are storing the volumetric flasks, make sure that you store the volumetric flask in an area where there is less likelihood of it falling over, or when you are placing a volumetric flask in your workstation as well, make sure there won't be any accidental tipping of the volumetric flask. If you keep it very close to yourself when you are handling something else, the chances of you accidentally knocking it over is greater. So please make sure when you are handling a volumetric flask, or when you keep a volumetric flask in your workstation, not to keep it in an area where there's a lot of activities going on. You can keep it aside to make sure that you will not accidentally knock it over, because if you accidentally knock it over, it may break. When you are using a volumetric flask, usually volumetric flasks come with a ground glass joint. So what you see here over here is a ground glass joint, which is a standard size ground glass joint, which will accept a standard adapter or standard stopper like this. So you can close the volumetric flask with the use of a stopper like this. Sometimes you might come across glass stoppers like the one that I have here. Sometimes it may come with a plastic stopper like this. When you are using a volumetric flask, it is important to know how to use the volumetric flask. Usually students, we will use the volumetric flask when preparing standard solutions. You will have a primary standard with you, and you will measure a small mass of this compound, which is also known as the primary standard, with the use of a watch glass. Watch glasses are usually used to measure different types of solids. It has a slight concave shape. It is made out of glass, as the name suggests, and we will be using watch glass mainly to measure different masses of different substances, and sometimes we will also use it to cover beakers when we contain certain volatile substances in beakers. We can use these watch glasses to cover the beakers as well. Sometimes when you want to evaporate certain liquids, we can place that liquid or add some of the liquid onto watch glass and keep it out to stand in air for the evaporation to take place. However, there are so many uses for a watch glass. In this particular instance, we have used the watch glass to measure a certain solid sample, just to show you how we are going to be preparing a standard solution. Since we are just going to demonstrate how a solid is going to be transferred into the volumetric flask, we have not shown you how to measure the mass in this part of our experiment, because the focus is on how we are going to transfer a solid onto our volumetric flask. Usually when you make a standard solution, a very specific mass of the standard solution should be measured, and all of that standard solution in solid form that you have here should be transferred into our volumetric flask. So let's see how we transfer this solid into our volumetric flask. For that, we'll be using a funnel, and we'll be using a wash bottle as well. We place the funnel like so on the volumetric flask, but when you are adding water, you will lift the funnel a little bit up from the lip of the volumetric flask to make sure that there is enough space for air to escape when water is being added to the volumetric flask. After placing the funnel here, we can take our watch glass and hold it at a slight angle, and you can place it on our funnel like so. And now you can see I have lifted the funnel as well. While holding the watch glass and the funnel like this, you can proceed to add water to our solid. So you can see the solid will slowly get dissolved in water and will be washed down into the volumetric flask. After all of the solid is transferred into the volumetric flask, make sure to wash the watch glass thoroughly. Make sure to turn the watch glass the other way around and wash the bottom bit of the watch glass again to ensure that all of the solid is completely transferred onto our volumetric flask. After transferring all of the solid that was on the watch glass into our volumetric flask, we can wash the funnel with some distilled water as well, and then we can lift the funnel and wash the tip of the funnel with some distilled water as well. After that, we can keep the funnel aside, and now as you can see, the solid is there inside the volumetric flask. You can now mix the solid with water by swirling the volumetric flask like this. Make sure to hold the volumetric flask near the beginning of the neck of the volumetric flask. Do not hold it from the top and swirl it. This may cause the volumetric flask to break. So hold it from this area of the volumetric flask, and then you can mix it really well. After mixing it really well, when you do not observe any more solid particles in it, you can proceed to add more water. You can proceed to add more water, but when you're adding water, please be careful. When you reach the neck of the volumetric flask, if you add water without taking enough care, what will happen is this neck area of the volumetric flask will fill very suddenly if you keep up with the same phase that you used to fill the remainder of the volumetric flask here. If you try to fill the volumetric flask at the same rate, and when you reach this particular neck area of the volumetric flask, from there onwards, since the diameter of the neck area is very small, the volume will increase quite rapidly. So therefore, when you are adding water to the volumetric flask, you have to be very careful. After getting to the neck area of the volumetric flask, you have to be very much aware of where the calibration line is, or calibration mark is. In this particular volumetric flask, the calibration mark is over here. So we can add water all the way close to the calibration mark, but after you get close, very close to the calibration mark, you will stop adding water from the wash bottle, and you will allow this volumetric flask to sit for a minute, and then you can go and get a dropper to add the rest of the water. And when you allow it to stand for a while, if there are any water droplets on the upper walls of the volumetric flask, you are providing them enough time for them to come into contact with this meniscus over here. So thereby all of the water droplets that are present over here in the upper parts of the volumetric flask are also taken into account when you're making your final volume. After allowing it to sit for about 2 minutes, now I will be taking a small beaker and some distilled water, and with the help of a dropper I will be adding a few drops of water until the bottom of the meniscus aligns with the calibration mark. You can place the volumetric flask in a flat surface first, and then you can proceed to add water and make sure that you keep your eye in the same level as the calibration mark. Sometimes you may bring the volumetric flask to your eye level, but if you want to be very precise, you can place it on a flat surface and then add the last few drops of water with the use of a dropper, so that you have enough control over the addition of water. Now we have added exactly the right amount of water. You can see the bottom of the meniscus aligns perfectly with the calibration mark. Bottom of the meniscus aligns perfectly with the calibration mark. So this indicates that we have added exactly the right volume of water into this volumetric flask. After adding the right amount of water to the volumetric flask, you can place the stopper and then you can mix the contents in it by turning the volumetric flask upside down. By doing this a couple of times, you can mix the contents in it really well, and you can make sure that you have produced a homogeneous solution by mixing the contents in the volumetric flask by turning it upside down a few times. Now we have mixed it really well, and we have now produced a standard solution with a known concentration with the use of volumetric flask. Now students, when you are preparing a solution with the use of a volumetric flask, if you add a bit more water passing the calibration mark that you see over here, at that point you have added more water than required, and this solution is no longer going to have a very specific concentration because you have added a little bit of additional water. At that point, you can't quickly dive in with a dropper to remove the amount of water you have added because it has already come into contact with the rest of the solution. If you remove certain amount of water from the top, it might also remove certain amount of the primary standard that we have added earlier into this volumetric flask. So therefore, you can't just dive into it with a dropper and remove some water to make sure the meniscus aligns with the calibration mark. So if you add a little bit of extra water into our volumetric flask, please make sure to start this process over. Otherwise, you will not be having a standard solution with a known concentration. The standard solution will ever so slightly be diluted and therefore will not provide you with correct readings, or it will not be a standard solution with a very accurate concentration. So therefore, you will have to restart this process again. So when you're adding the last few drops of water into volumetric flask, please be very careful. And if you want to store this for future use, you can label the contents in it on the volumetric flask and keep it for later use. Now we have prepared a solution of HCl with the use of concentrated HCl that we have over here. We have calculated the volume of HCl we should take from this stock bottle, and we have transferred that volume into our volumetric flask, and we have now prepared a standard solution of HCl with a concentration of 0.1 moles per decimeters cube. Now we are going to observe how the titration can be done with the use of this solution. Over here, students, we have another volumetric glassware which is known as a burette. A burette is used to dispense small volumes of a solution or a liquid gradually onto a titration flask. Burettes are mainly used for titrations. However, burettes can be used to dispense small volumes of liquid to any reaction mixture. So, if you take a look at the burette, the top end of the burette has a rating 0 and the bottom end reads 50. Most burettes can hold 50 cubic centimeters of liquid or of solution, and as you open this valve here, which is also known as a stopcock, liquid will be poured down from the tip of the burette here, and as the liquid pours down, you can find out the amount of liquid that is released from the burette by reading the calibration mark that aligns with the bottom of the meniscus. Now, if you observe, the smallest reading over here is 0.1 cubic centimeters or 0.1 milliliters. So therefore, if the meniscus aligns between two lines, you can also measure 0.05 cubic centimeters with the use of this burette as well. So after learning about the main key important parts of the burette, we can now move on to how to use this burette. Before using a burette for any titration, students, you need to fill the burette. So to fill the burette, you first need to wash the burette. Now the burette that I'm currently holding is washed with distilled water, or before that it was washed with detergent and with tap water, and finally with distilled water. And after that, before using this washed burette, we are going to have to wash this burette once more with the solution we will be using for the titration. So in this titration, we are going to take the hydrochloric acid into our burette. So we will be washing our burette using this 0.1 moles per decimeters cube HCl. We do this to ensure that the interior walls of the burette is completely coated with the HCl. If there ever happens to be just a drop of water, even this simple drop of water can dilute the standard solution that we include in the burette. So to eliminate this type of dilution, we will be washing the interior walls of this burette using HCl. So if there happens to be any droplets of HCl in the interior walls of this burette, when we add HCl to it, there won't be any dilution happening, because even the droplets of water that you find in the burette will have the same concentration of this HCl solution. So it is always a good practice, and it is always important to wash the burette with the solution that you're going to be taking into the burette. To discard the washings, we will take this beaker over here. So after washing the burette, we can discard the washings into this large beaker we have here. And now let's take another small, very clean and dry beaker, and we will add our HCl solution to this clean dry beaker. And now we will take our burette and we will make sure the stopcock is closed so that whatever the solution we include in the burette won't leak out of the burette tip. So we will make sure that the stopcock is closed tightly, and then we can bring the opening below our eye level, and we have to use a fresh funnel or clean dry funnel to add small amount of HCl into this burette. Now, as you can see, we have added some HCl. You can then turn it to a horizontal position like so, and you will gently rotate it, making sure that the entire interior wall is coated with this HCl solution. And as you do that, if some spilling may to occur, you can allow that to happen by placing the opening or the upper opening of the burette over the discard beaker. This beaker will collect all the discarded HCl. So after washing the interior walls of the burette the way that we did earlier, we can then open the burette to allow all of the remaining HCl to run through the tip of the burette. We can open it suddenly so that the entire volume runs through the tip of the burette without leaving any air bubbles or without leaving any residual HCl on the tip. Now, after sending out all of the HCl, we have now washed our burette with HCl. Then the next step would be to fill the burette by placing it in a burette holder like so, and then whenever you are filling a burette, you should not be taking whatever the solution above your eye level and above your head to fill the burette. It is not going to be safe for you to do that. So therefore you have to bring this burette to a stool or to a table that is shorter than the workbench, so that you can have the opening or the top of the burette below your eye level. Now we can bring this burette below eye level, and we have a funnel that we used earlier to fill this burette with HCl. We'll place the funnel like so. And then we can proceed to add HCl slowly into our burette. Now, one of the very important things to do when you are filling the burette is always to make sure the stopcock is closed tightly. Otherwise, some of the HCl you add or whatever the solution you add might leak from the tip of the burette. So to avoid doing that, make sure each time when you are filling the burette that the stopcock is tightly closed. And whenever you are filling the burette, lift the funnel up a little bit. Otherwise, when there is a seal created like this, when you are adding the HCl solution or whatever the solution you are filling into the burette, the gas that is displaced by the incoming volume of liquid is going to go out of this burette through the same opening of the funnel. So liquids going in and the gas going out will both happen from the same opening of the funnel, which would create the liquid to splash from the funnel. So to avoid that from happening, you can lift the funnel up a little bit so that there is an air gap over here for the displaced air to go out of the burette. So while lifting it up, you can add HCl. And students, when you're filling the burette, please make sure to add more than adequate volume of HCl above the zero line of the burette. This is to make sure when you are using the burette, you need to make sure that there are no air bubbles trapped in the burette tip. So to make sure that there are no air bubbles trapped in the burette tip, we need to open this stopcock quite suddenly, making sure all of the air bubbles that are trapped here gets rushed out or pushed out of this burette tip. If there are any air bubbles, due to the compressibility of these air bubbles, it might produce inaccurate readings when you are trying to measure different volumes that have been dispensed through the burette. So we will open this stopcock real fast and we'll see how this area of the burette is going to be filled with the HCl solution. When you're handling the burette, you need to handle the burette from your left hand if you are a right-handed person, and you have to make sure that you don't fiddle with the stopcock from your right hand, because you might exert a stronger force and the burette might break, because this area of the burette is quite weak. So therefore you usually handle it from your left hand. But to show you how this area of the burette gets filled with solution, I will use my right hand for this particular instance. Do you observe any air bubbles in this region? We do not. So when you open it little by little, we can't see any air bubbles coming in and out in this region, meaning there are no air bubbles in this region as well. So at that point, we have successfully filled the tip of the burette as well. Then you can bring the burette again to a stool or a table that is shorter than your workbench, and you can observe the bottom end or bottom line of the meniscus aligning with your zero line. So you have to open your stopcock, and little by little you can allow the liquid to go down while making sure that the bottom of the meniscus aligns perfectly well with the zero line. So now students, you can very clearly observe that the bottom of the meniscus has now perfectly aligned with the zero line of the burette. Now this means we have correctly filled our burette, and you can place the burette again in your workbench, and we can keep all of the other equipment we do not use out of our way. And now we will be moving on to withdrawing some sodium hydroxide from our sodium hydroxide solution we have over here. So when you are conducting an experiment, we need to take this type of titration flask. You can see it has a conical shape and a wider mouth or wider opening. So this allows us to insert the tip of the burette halfway through the opening, or it will not be positioned like this, but we can actually keep it positioned like so. So when you have the HCl added onto this titration flask, it is easier for us to mix the contents in it when you have a wider opening, as well as when you're using a volumetric pipette, we need to make sure that the tip of the volumetric pipette touches the internal wall of the container that we are transferring the contents into. So when you have a wider opening, it is easier for us to insert this volumetric pipette and transfer the contents into the titration flask like this. If the opening was smaller, it would have been more difficult to transfer the contents from the volumetric pipette to our titration flask that we have over here. Then students, due to the slanted walls that we have of the titration flask, when we are mixing contents in it, there won't be any splashing happening, or the contents in it will not be easily splashed out due to these slanted walls that we have over here. When carrying out titration, we usually have a solution that we know the concentration of, and that is usually known as the titrant. And the titrant is generally taken into the burette so that we can add the titrant in a more controlled manner to the solution which we don't know the concentration of. So in a titration, we have one solution we know the concentration of, which is known as the titrant, and we have another solution which we don't know the concentration of, and that is referred to as the titrand, ending with a D, right? A titrand. Titrand is usually taken to the titration flask. So in this case, the sodium hydroxide, we don't know the concentration of it. So we have the titrant here, which is the sodium hydroxide with unknown concentration, and we need to transfer a known volume of this sodium hydroxide solution with a unknown concentration into our titration flask. So to do that, we will take a clean beaker and we will transfer around 50 milliliters into this beaker, and to transfer an accurate volume of this sodium hydroxide into the titration flask, we can use a volumetric pipette. This is a volumetric pipette. In a volumetric pipette, you are going to have a glass tubing with a small bulbous area and one single calibration mark. So this calibration mark would read very accurately 25 milliliters. When it comes to this particular volumetric pipette, it can measure exactly 25 milliliters or 25 cubic centimeters. So when you're using this volumetric pipette, we can very accurately measure exactly 25 milliliters of the solution. And in order to measure the solution very accurately, the bottom of the liquid meniscus should align with the calibration mark that is etched onto this volumetric pipette over here. Due to the volumetric pipette having this cylindrical nature, you should not be placing it on the table without two or more different objects stopping it from rolling over. If it rolls over, it may fall off of the edge of a table. So to prevent it from happening, you need to make sure that it is placed in an area where it is not possible for the volumetric pipette to roll over the edge of the table. Apart from that, when you are handling a volumetric pipette, since it is a very long, slender glass tube, if you mishandle it, there's a high chance of it breaking. So you have to be very careful when you're handling this type of long pieces of glassware. This pointed end is the opening or the tip of the volumetric pipette, and to this upper end we can connect a pipette filler. I will explain how this three-way safety pipette filler is used later on, but for the time being you have to know when you're filling the pipette with liquid, you will have to use a pipette filler. Do not use your mouth to suck the liquid onto a pipette. It is not a safe practice. You have to always use a pipette filler. Apart from the volumetric pipette, we also have these graduated pipettes where you can see there are graduation lines all the way from 0 to 10. So this will allow you to measure varying volumes of liquid. In this particular graduated pipette, you can measure volumes ranging from 0 to 10 milliliters. If you want to measure any volume of liquid ranging from 0 all the way up to 10 milliliters, you can use this graduated pipette. Now, let's learn about how we can use this pipette filler. The pipette filler, this particular type of pipette filler is known as the three-way safety pipette filler. This has three main buttons. We have up on top a button usually labeled with an A to indicate this is the button you need to press when you are releasing the air in the bulb that we have over here. This pipette filler is squeezable, and when you squeeze it, all of the air inside the pipette filler can be released if you press the top button over here and squeeze it. So if you press this top button, which is usually labeled A, in this case you don't find the labelings, but usually it is labeled A. So A stands for air. So basically, if you want to remove all of the air inside this bulbous area of the pipette filler, you can press this button, and this is actually a valve that you have here. When you press this button, the valve will open and all of the air will exit through this opening that we have over here. And there is another button over here which is usually labeled S. S stands for suction. So when this pipette filler is connected to the pipette like so, when you press this middle button that you have over here, it will suck the liquid through the pipette all the way up to the calibration mark. And if you allow it to if you keep pressing this button, sometimes the liquid may rise above the calibration mark and it might also enter the pipette filler. So take precaution not to do that. Once the liquid level is right at the level that you want, you can stop pressing this suction button. And there is another button that is over here that is going to be usually labeled E, indicates emptying the pipette that we have over here. So when you want to empty the pipette, when you want to release the liquid that is are held in the pipette, you can press E. When you press this particular valve over here, the liquid in the pipette will be released. So now that we have learned about how to use the pipette filler, we can transfer exactly 25 cubic centimeters of this solution into our titration flask. So let's proceed to do that. Let's press this button over here and squeeze this area so that the bulb is now squeezed and it doesn't have enough air in it. But when we place the tip of the pipette into the beaker and press this middle button that is usually labeled S, it will suck the liquid through the pipette tip into the pipette, and we have now taken more than the necessary volume of sodium hydroxide, and by pressing this E button, there's a third button over here, and by pressing the E button we can drop some of the liquid we have taken in. So we went below the right amount, so we can gradually suck small amount of liquid into the pipette and make sure the meniscus aligns perfectly well with the calibrated line and fill the pipette accurately. Right now you can see the bottom of the meniscus aligns perfectly with the calibrated line. Now students, after filling it up to the correct calibration mark, we are going to place the pipette tip in this manner where the pipette tip is in contact with the interior wall of the titration flask, and then we can press the button to empty the contents in the pipette while making sure the tip of the pipette is in contact with the interior wall of the titration flask. Now you can see that all of the liquid is now transferred into our titration flask. Another very important fact to keep in mind is, students, you should never push this final bits of liquid that is trapped in the tip of the pipette. The pipette is calibrated in such a way that it has accounted for the small amount of liquid that gets trapped on the tip of the pipette. So in the tip of the pipette we have a small amount of liquid trapped here, and that amount of liquid is accounted for when the pipette was calibrated, so there's no need to blow it out into the titration flask. We have accurately transferred exactly 25 cubic centimeters of HCl into the titration flask, and it is supposed to leave this one single drop on the pipette tip. There's no need to blow this single drop of liquid onto your titration flask. If you do so, at that point you have to know your measurement over here is incorrect, because you have now added an extra drop of HCl into your titration flask. So after making sure that you don't push the last drop that is trapped in the pipette tip into the titration flask, we can now move on to carrying out a titration. When you are carrying out a titration, you have to usually use an indicator. In a strong acid, strong base titration like the one that we are carrying out, we can use phenolphthalein as an indicator. So we have phenolphthalein here. We are going to add a few drops of phenolphthalein into our sodium hydroxide here. In the presence of sodium hydroxide, phenolphthalein is going to change its color to a pink color. and we are going to use a white color tile to see a very clear color change when we are carrying out a titration. We will be slowly adding HCl onto the sodium hydroxide until this pink color completely disappears from this titration flask. When you observe a colorless solution, at that point we will end this titration and we will record the reading. That is how we will carry out a titration. When you are operating the stopcock of the burette, make sure to operate it in such a manner where you don't use your dominant hand directly like so. You will place your non-dominant hand over the stopcock like this, and you will slowly rotate the stopcock and open the valve, allowing few drops of HCl to come into contact with our sodium hydroxide at a time. And after adding few drops of HCl, you can take your right hand and you can start swirling the contents in the titration flask and mix the contents really well. You can continue to add small amounts of HCl while swirling like this until the pink color completely disappears. You can see the pink color is not as strong as when we started to do the titration. And now students, we are close to the end point. You can see when you add a few drops of HCl, you can see it takes a while for the pink color to disappear, and now you can see little by little the pink color completely disappears after the addition of the last drop of HCl. Now students, in this part of our experiment, we learned about how we can use a titration flask, volumetric flasks, volumetric pipette, graduated pipette, and a burette. And we even carried out a titration to show you how a titration is carried out. So by now you should have a good idea about using this common lab glassware. So we have a few more glassware to take a look at. So let's move on to the next set of glassware. Now students, we are going to take a look at how to use a measuring cylinder and separatory funnel. Let's first take a look at measuring cylinders. We have different measuring cylinders here that can hold different volumes in them. Depending on the measuring cylinder that you use, the smallest volume or smallest unit in the measuring cylinder may vary. You have to observe the calibration marks or graduation lines that we have over here and observe the smallest unit found in that particular measuring cylinder. When using measuring cylinders, please take precaution to, when you keep the measuring cylinders in your workbench, please keep them in an area where you will not easily knock them over. Since these measuring cylinders are quite tall, if you are moving about, if you move your hands a lot while conducting your experiment, you may accidentally knock one of these measuring cylinders over, and due to its long narrow body that it has, it is easily able to tip over, or you can easily knock one over and damage the measuring cylinder. So when you are handling them, after handling them, keep it away from the main working area so that you will not accidentally knock one over. Just like in any volumetric measurement, when you are filling the measuring cylinders, you have to make sure the bottom of the liquid meniscus aligns with the required calibration mark. In this case, if you want to measure 10 milliliters or 9 milliliters, the bottom of the meniscus should align with the 10 milliliter line if you are planning on measuring 10 milliliters. If you're planning on measuring 7 milliliters, the bottom of the meniscus of the liquid should align with the 7 milliliter mark. Now, you cannot use measuring cylinders to heat substances in it. You normally don't use measuring cylinders to mix things in it as well. We only use measuring cylinders to accurately measure volumes of different liquids or solutions. We will be able to transfer them from one place to another. However, main purpose of a measuring cylinder is to measure different volumes accurately. It is not used to mix things, or the primary purpose of a measuring cylinder is not to mix things or hold things for a prolonged period of time. We can transfer the substances you want to measure here. You can take the measurement and then you will be transferring it to your reaction mixture or your desired container. So that is the use of measuring cylinders. Students, when handling measuring cylinders, as I mentioned earlier, since this is volumetric uh, glassware, be careful when handling it. The calibration lines that are in beakers and conical flask, titration flasks, are not very accurate. We only use them to develop a rough idea about the volume that is present in those glassware. If you want to accurately measure a volume, you have to use a measuring cylinder. The other volumetric glassware that we have learned about so far is the graduated pipette, volumetric pipette, and the burette. Now we have learned about the measuring cylinder as well. It is also known as the graduated cylinder. So now, after going through these graduated cylinders or measuring cylinders, we can now talk about a separatory funnel. You can see over here we have a separatory funnel. Separatory funnels are usually used to separate two immiscible liquids. When you are carrying out solvent extractions, you will most often have two immiscible liquids mixed together, and if you want to separate two immiscible liquids, you can use a separatory funnel. Separatory funnel has a stopcock which will allow you to retain whatever the contents that you include in this area of the separatory funnel without them running down through the tip of the separatory funnel. And you have a stopper here to make sure the contents in it will not get evaporated, or the contents of it will not be leaked when you turn the separatory funnel upside down. When you carry out solvent extraction processes, we usually fill the separatory funnel with the immiscible reaction mixture, and then we will hold the stopper of the separatory funnel like this, and while making sure the stopcock is tightly closed, we are going to mix the two immiscible liquid layers together by shaking it thoroughly. And when you shake it, sometimes due to evaporations that take place, certain amount of the liquid might evaporate, which will cause the gas inside, which would cause the gases to accumulate inside the separatory funnel and cause pressure buildup. To relieve the pressure after you mix it really well, you can turn it upside down and you can open the stopcock, allowing the gas to be sent through this area, relieving the pressure. Another way of relieving the pressure would be to open the stopper from the top over here. So in order to do that, after mixing it really well, you will turn it upright once more and we will open the stopper over here, which will allow the accumulated gases to get released from the separatory funnel, and then due to that the pressure inside the separatory funnel will be relieved. If you don't relieve the pressure as you mix it, what will happen is, due to the pressure that is accumulated in the separatory funnel may crack, or there could be fractures that are happening on the glass of the separatory funnel due to the high pressure that is built inside the separatory funnel. Now let's place the separatory funnel here, and we are going to be moving on to observing how we can use the separatory funnel to separate two immiscible layers from one another. Now let's take a clean beaker here and let's add a few milliliters of vegetable oil. We can add about 10-15 milliliters, since we are going to demonstrate how the separation is taken place. You don't have to measure a very specific volume of coconut oil here. So now we have taken about 10 to 15 milliliters of coconut oil, and to that we can add 25 milliliters of water. Again, students, you don't need to be precise here because this is just a demonstration, but when you are actually carrying out experiments using the separatory funnel, you will need to use very specific volumes, especially when you're carrying out solvent extractions. The solvent that is going to be used should be measured accurately with the use of a measuring cylinder. So to indicate that, we are going to measure 25 milliliters of water. In this beaker we have distilled water. We are going to measure 25 milliliters of distilled water with the use of a measuring cylinder. When you are using a measuring cylinder, it is always best to keep the measuring cylinder on a flat surface, and then we can add whatever the liquid that you want to measure. If you want to add the last few cubic centimeters of water with a bit more control, you can use a wash bottle and add water little by little. You can bring your eye level close to the 25 milliliter mark, and you can slowly add few drops of water with the use of a wash bottle, and at the point at which you see that the bottom of the meniscus align well with the 25 milliliter mark, you can stop adding water. Now as you can see, the bottom of the meniscus aligns perfectly with the 25 milliliter mark. So now we have measured exactly 25 milliliters of water. We can now proceed to add this to our oil that we have over here. Now students, we have a mixture of oil and water here, and we are going to see how these two immiscible layers can be separated with the use of a separatory funnel. Separatory funnels are usually supported by these ring clamps we showed earlier when we were talking about funnels. Also, we use the same ring clamp. Now we are holding a separatory funnel with the use of this ring clamp. Before adding this uh, water and oil mixture to the separatory funnel, we have to make sure that the separatory funnel is tightly closed so that none of the uh, water oil mixture actually runs down the tip of the separatory funnel. After making sure that it is tightly closed, we can add mixture into our separatory funnel. After adding the mixture, we'll show you how, if you ever wanted to mix these two layers a bit more, especially when it comes to solvent extraction processes, you will need to mix these two layers a bit more before separating them out. So when you want to mix them really well, you will hold the stopper tightly, making sure none of the liquid will escape from this area, and you will shake it like so. As you can see, the contents in it is now going to be mixed really well. Afterwards, you can relieve the pressure by turning it upside down and opening this stopcock. Or else, you can relieve the pressure by removing the stopper as well. After mixing the two layers together, you can leave it for a while for the two layers to separate once more. When the two layers are separated, the two layers will appear clear again. Right now it appears cloudy. When the two layers are separated, it will appear clear. Now students, we are going to open this stopcock and allow the water to uh, get collected into the beaker over here. But before we do that, please keep in mind, if you keep the stopper closed over here, as the liquid runs down, due to a vacuum being created here or due to the pressure lowering here, you will not be able to easily dispense the bottom layer into the beaker here. So always remember to remove this stopper and then slowly turn the stopcock, allowing the bottom layer to get collected into the beaker here. You can see as the bottom layer empties out into this beaker, the water oil interface gets closer and closer to this area where the stopcock is. At that point, when the interface comes into contact with the stopcock, you can close this stopcock and you can extract the water layer into one beaker. There will be a small amount of water still remaining here. If you want to obtain that as well, you can open this valve slowly and remove that amount of water as well. But keep in mind, oil water interface is still here. Again, very slowly you can observe how the oil water interface comes all the way to the end over here. Now students, we have carefully removed all of the water from the separatory funnel, and with a fresh beaker I can now collect the oil layer into a separate beaker. In this way, we can separate two immiscible liquids with the use of a separatory funnel. Now keep in mind students, this is how we will be using a separatory funnel to separate out two immiscible layers of liquids. After learning about how to use this separatory funnel, you need to move on to learn how to use a distillation setup. So let's have a look at how to use a Libby condenser along with a distillation flask in the next step. Let's learn how to use a Libby condenser along with a distillation flask in our next experiment. In this part of our experiment, we are going to learn how to use a round bottom flask, a flat bottom flask, and a Libby condenser. So students, these round bottom flasks that you see over here are usually used to mix different types of chemicals and carry out reactions, and mainly used in distillation setups. Due to this spherical or round nature of this flask, it can evenly distribute heat when heated with appropriate heating sources. If this is heated using a water bath, due to this spherical shape, heat will be evenly distributed into the sample that is contained in the round bottom flask. You can use round bottom flasks in heating mantles as well, and due to this spherical shape, it can withstand a certain amount of high pressures or vacuum pressures as well. So therefore, we will be using round bottom flasks when it comes to distillation setups. Apart from that, round bottom flasks cannot stand on their own, as you may have noticed, due to the round bottom that they have. So it has to be supported by a stand or by a cork ring. Sometimes you have cork rings that will allow these round bottom flasks to stand on their own when placed on a cork ring. Over here we have supported this round bottom flask with the use of a tripod. Apart from the round bottom flask, we have this flat bottom flask. What we have over here is a flat bottom flask. You can see the bottom of this flask is flat. So these flasks can stand on their own without the help of a support. So therefore, we can use this type of flat bottom flasks when it comes to mixing different chemicals as receiving flasks. And due to the narrow neck that we have over here, it can easily be clammed. That goes for round bottom flasks as well. These can be clammed easily due to the narrow necks that they have. And when it comes to the flat bottom flask, since it has a flat bottom, it can be placed on a Bunsen burner with a tripod and a wire gauze or wire mesh. So you can generally heat these flat bottom flasks using a Bunsen burner and wire gauze as well. But compared to round bottom flasks, the heat will not necessarily be distributed evenly when we are talking about a flat bottom flask. And due to this flat bottom, it cannot withstand vacuum pressures or pressures when applied with pressures. Due to having this flat bottom at the end, it cannot withstand high pressures like the round bottom flask can. Therefore, in certain applications, we will be using round bottom flasks, and when it comes to certain applications, we will be using the flat bottom flask. And both of these flasks are good lab equipment that can be used when it comes to mixing substances due to the spherical nature of the flask and the long neck. There's minimum risk of splashing contents over, so therefore we can use these round bottom or flat bottom flasks when it comes to mixing things thoroughly as well. Again, when you are handling these types of lab equipment with long necks, please take precaution to not knock these things over. They will easily break if you knock them over. So after using them, keep it away from your work area so that you will not accidentally knock them over. And over here we have a Liebig condenser. Liebig condenser is mainly used to condense or cool down vapor that is traveling in the interior column of the Liebig condenser. There is two main compartments in a Liebig condenser. There's an inner tube that will carry vapor in it, and then there is an outer jacket that is carrying water in it. So over here you can see there are two tubings connected to the Liebig condenser. The bottom tube that we have over here brings in water. We have now turned on the water supply. So very slowly the bottom water inlet brings in water to the Liebig condenser, and you can see the water is traveling upwards and it exits from this outlet over here and will be taken out of the Liebig condenser through this rubber tubing. When we have this setup fixed in this particular manner, the cold water that enters here travels upwards and is going to be exiting from the outlet here. And we have hot vapor produced here in this area, and that vapor is directed into the inner tubing of our Liebig condenser, and this vapor is going to be directed into the condenser, and the inner tube of the condenser will carry really hot vapor. Water comes into the condenser from the bottom and exits from the top to make sure that there is maximum heat transfer when vapor is traveling from over here all the way to the end of the condenser. When cold water enters through the bottom and exits through the top, there is maximum amount of heat transfer happening from the vapor to the water. So therefore vapor will condense into a liquid once more, and the condensed liquid will be coming out of the tip of the condenser, and to collect the liquid we can place a beaker, or in this case we have placed a flat bottom flask. So when you turn on this Bunsen burner, or when you light up the Bunsen burner, we have a distillation flask that is fixed over here in this retort stand. So this round bottom flask is a special round bottom flask that is mainly made for distillation purposes. The round bottom flask has a side arm that can be connected to a condenser. So this round bottom flask is known as a distillation flask. We mainly use this distillation flasks to carry out distillation, as the name suggests. As we provide this distillation flask with some heat, the contents in this distillation flask, majority of the time it will be a mix of two components. For example, if you are talking about miscible liquids, there will be one liquid that has a lower boiling point, another liquid that has a higher boiling point, and the one with the lower boiling point will get vaporized at a lower temperature than the one with the higher boiling point. So the one with the lower boiling point will get evaporated first and will come into this area, and you can observe the temperature of the vapor with the use of a thermometer that we have over here, and you will be able to ensure that you are separating out the component with the lower boiling point by observing the temperature over here. If it reads, or if it gives you the boiling point value of the component that has the lower boiling point, then that means what is being separated over here as a vapor is the component with the lower boiling point. So when we have a mixture of water and ethanol, what will get vaporized first? Ethanol has a boiling point of 78 degrees Celsius, so ethanol will get vaporized first. So therefore, at around 78 degrees Celsius, initially the ethanol component of the mixture will get vaporized, and you will see the vapor having a temperature of the boiling point of ethanol. So therefore, the thermometer will read 78 degrees Celsius while ethanol is being boiled. So ethanol vapor will be directed into this condenser, and as ethanol vapor passes through this condenser, it will get cooled down due to the water that is circulating around this inner tube. So therefore, as ethanol vapor passes through this inner tube, the vapor will cool down and will get condensed into a liquid, and you can see the liquid getting collected over here, and it will get collected in this flat bottom flask. So after a while, when all of the ethanol is completely boiled off, then when there's only water remaining, you will see the temperature of the thermometer going above 78 degrees. This will indicate that all of the ethanol is now boiled off, all of the ethanol is now removed from the mixture. When you see a temperature higher than 78 degrees Celsius, that will be the time for you to remove this setup from heat, and you can remove this collected amount of ethanol from here as well and conclude your experiment. So students, we have in this distillation flask a mixture of water and ethanol. So we will now light up our Bunsen burner and initiate this distillation process. As you distill ethanol from water, you will see the temperature of the thermometer will remain at around 78 degrees Celsius, and we will see ethanol getting collected over to this flat bottom flask we have over here. Now students, we have started heating up this distillation flask, and you can see little by little the temperature of the contents in the round bottom flask will increase, and at one point the ethanol will get vaporized, and that vapor will enter this condenser, and it will cool down as it passes through the inner tubes of the condenser, and it will get collected onto our flat bottom flask here. Now take a look at this. This is at 78 degrees Celsius. So this is how we will be carrying out a distillation. Now students, as you can see, the vapor that is produced is entering this condenser, and as it passes through the condenser, you can see the vapor turns into a liquid, and it gets collected over here at our flat bottom flask. You can see little by little the vapor condenses and gets collected in our flat bottom flask. So this is how we will be carrying out a distillation setup. So as you can see earlier, the temperature remains at 78 degrees Celsius because, as I mentioned earlier, the temperature would not change until all of our ethanol component is vaporized, and after all of the ethanol component in our mixture is vaporized, then you will see the temperature increasing. So students, this is how we would set up a distillation setup. Now we learned the uses of the round bottom flask and the flat bottom flask, as well as our condenser, and how to set up the condenser, especially making sure that we allow the water to go in from the bottom of the condenser and water to come out from the top of the condenser. We can see some amount of ethanol has been collected over here. Now this is how our distillation setup is going to be fixed and how distillation is going to be carried out. When you want to stop the distillation, you can remove the heat source from the setup. But keep in mind, students, you are not supposed to, as soon as removing the heat, you are not supposed to dismantle this setup, because there will be a certain amount of pressure generated within this distillation flask. So attempting to remove it now could sometimes cause splashing of the contents in the round bottom flask, and sometimes it could even cause some of the equipment to break. So therefore, you will wait until the setup comes to room temperature or it decreases in temperature, and when the pressure within the system has come down, then you can remove this setup or dismantle the setup and clean and store this equipment in the relevant places. So when you are conducting such an experiment, you have to take precaution, especially when you are dismantling such a setup. You have to wait till it cools down. You are not supposed to dismantle it when it is hot. So these are the main information that you need to keep in mind when handling a round bottom flask, flat bottom flask, or a condenser. And when you are using a distillation flask, it is easier for us to connect the condenser to the distillation flask and carry out a reaction. And on top of this distillation flask, you can see a rubber stopper connected to a thermometer. This will allow us to measure the temperature of the vapor that is produced. So that is how we use these three lab equipment or these three glassware. Now let's move on to another equipment. Now students, we are going to look at what is known as Buchner funnel. Now earlier on in a previous part of this experiment, we discussed how to carry out a filtration. If you have a solid liquid mixture, you can filter it with the use of a filter paper and a funnel. When you use that particular setup, we will be filtering with the use of gravity. So we call that gravity filtration. Gravity filtration, we solely depend on the force of gravity to carry out the filtration. So the liquid is going to be separated from the solid through gravity. So this sometimes may take some time. So therefore, to avoid spending a lot of time filtering liquid from the solid, we can use a vacuum filtration system. So what we have here is a vacuum filtration method that we carry out with the use of a very specific type of flask known as a Buchner flask. Now, this Buchner flask is a special type of flask which we'll be using only for vacuum filtration. This Buchner flask is made of a little bit of a thicker walled glass compared to other conical flasks that we have come across in the previous parts of this experiment. And apart from that, there is a separate arm coming out from this Buchner flask to connect this Buchner flask to a vacuum pump. So apart from the Buchner flask, we have another ceramic flask that is going to be attached to the Buchner flask, which is known as Buchner funnel. What we have here is a Buchner funnel which contains perforations at the bottom plate of the funnel, and as you can see, there is a rubber stopper connected to this funnel to provide a proper sealing effect when we connect this Buchner funnel into our flask. So this Buchner funnel will be connected to the Buchner flask like so, ensuring that there is a proper seal between the funnel and the flask. And Before we connect this to the vacuum pump and turn on the vacuum, you will be placing a filter paper on top of this Buchner funnel, covering all of these holes of the Buchner funnel. You have to take a filter paper of an appropriate size, otherwise you will not be able to cover all of these holes in the Buchner funnel. You have to make sure all of the holes are completely covered. It should not leave any of these holes open once you place the filter paper on the Buchner funnel. After covering all of the holes with the filter paper, you can connect this arm to a vacuum pump and you can start to vacuum filter whatever the contents that you want. However, before transferring your solid liquid mixture onto this Buchner funnel, always carry out the additional step of wetting the filter paper with the solvent found in your liquid solid mixture. So if the liquid solid mixture is water based, you are going to wet this filter paper with water, and if the liquid solid mixture is made of an organic solvent, you are going to use that organic solvent to wet this filter paper first. Then after turning on the vacuum pump, you can transfer the contents onto the Buchner funnel and carry out the filtration process. Due to the vacuum that is going to be created when this is connected to the vacuum pump inside this Buchner flask, the filtration will happen much faster compared to the use of gravity filtration. So filtration will happen much faster, and the solids that are going to be remaining on the Buchner funnel over here is going to be even dried a little bit as well due to this vacuum action that is going to take place in this Buchner funnel. So Buchner funnel is not only used for faster filtration, but also is used for partially drying the solid that is going to be found over here, and it's going to be easier to scrape off the solid that is filtered over here compared to the removal of the solid when it is filtered using gravity filtration. Apart from these main points revolving around the Buchner funnel, you need to keep in mind, if the liquid travels through the Buchner funnel extremely fast, that means there could be a tear of the filter paper that we have placed inside the Buchner funnel, or the filter paper might have gotten folded, revealing some of the holes in the Buchner funnel. This could create a small area in which the liquid solid mixture can go through the funnel without getting filtered properly. You can very clearly see it. At that point, there will be some solid particles coming into this area of our Buchner flask. So you can see solid particles here if we have done this incorrectly. When the filtration is taking place, you will not see any solid particles in the Buchner flask. All of the solid will remain on the Buchner funnel. If there are any solid that has entered into the Buchner flask here, that means there is some error in the filtration process. You will have to carry out the filtration again. When you constantly keep adding your liquid solid mixture, you have to take precaution. If the liquid level inside the Buchner flask comes all the way up to where the arm is, that is over here, at that point the liquid can get drawn into the vacuum pump. This could cause malfunction. So therefore, students, when the liquid level goes up, you turn off the vacuum pump and you will remove the contents inside this Buchner flask into a different container, and you will repeat the same process again. Sometimes you would want to obtain the filtrate, or sometimes you would want to obtain the solid. Both of them can be obtained in this filtration process, just like gravity filtration, but this filtration is much more efficient and faster compared to gravity filtration. Now students, these are the main uses of Buchner funnel and the Buchner flask, and when you're using it, how you should be using it, and the precautionary measures revolving around this particular glassware was mentioned in this part of our experiment. Now let's move on to some other equipment we will be using in the lab. Now students, we are going to take a look at few equipment that are made out of ceramic materials. So we have here crucibles with lids. So these crucibles are capable of withstanding really high temperatures. So therefore, when you need to heat a specific substance to really high temperatures, you will not be using a boiling tube or a test tube, a beaker or a round bottom flask. Instead, you will be using crucibles. And if you want to have a more controlled reaction taking place, you'll be using crucibles with lids. So these are ceramic crucibles. We will be using crucibles with lids if you want to have a more controlled reaction taking place when you are carrying out a reaction with the help of a crucible. Now, crucibles are equipment that are going to be heated to really high temperatures. So when they are heated, how are we going to handle them? Are we going to lift them up with our fingers like this? Is it going to be possible to touch them? The answer would be no. These will be heated to really high temperatures. So at that point, handling them with your hands is going to be impossible. So therefore, we will be using a pair of tongs. Students, so when you are handling crucibles, you have to be extremely careful not to burn yourself by accidentally grabbing the crucible with your hands. Please avoid that at all costs. When you are handling your crucibles, you have to make sure that you handle the crucible with a pair of tongs so that you will not get burned when you take it on and off the heat. So what you have here is a pair of tongs. This is essentially equipment that is designed for grabbing things. Usually we use pairs of tongs like this to grab really hot objects like crucibles. If you want to grab a more fine type of object, you can use forceps. Usually in the chemistry lab, we will use forceps to grab very fine crystals or very fine substances or smaller substances. However, forceps are mainly used in biology labs where they have to use with very fine material. So when you are handling very fine, or when you need to grab very fine particles, you can use a forceps in the lab. Now, to demonstrate how we can use a crucible, we are going to carry out a small experiment where we will be burning a piece of magnesium and producing magnesium nitride. When you burn magnesium in air, it mainly reacts with oxygen, but it can also react with nitrogen in air to form magnesium nitride. But since when you burn it in open air like this, since there is enough and more oxygen, the amount of magnesium oxide produced will be greater than the amount of magnesium nitride produced. So therefore, one of the things we can do is we can carry out this particular burning of magnesium strip in a crucible, or we can actually heat the crucible with the magnesium strip in it until it reacts sufficiently with the nitrogen in this closed container. We will close the lid after placing the magnesium strip. So in the closed container, it will react with the nitrogen in it. After the oxygen runs out in this area, the remaining amount of nitrogen will react with the magnesium strip and will produce more magnesium nitride. And students, keep in mind, crucibles are mainly used to carry out melting or ashing experiments because it can withstand really high temperatures. We can carry out ashing or melting related experiments with the use of crucibles. And when you're providing heat to the crucible, we can use a Bunsen burner. And since we are going to be heating it up to really high temperatures, we can use a clay triangle like this to hold the crucible in place. These clay triangles are going to be placed on a tripod or any other stand that can support it, and we will be placing our crucible on our clay triangle. This way, really high temperatures can directly be provided onto our crucible here. If you use a wire mesh, the high temperatures sometimes might cause the wire to melt, but that will not happen when you have placed the crucible in a clay triangle like this, and when you are directly heating the crucible, there won't be any type of accidents taking place due to the melting of the wire mesh. So do not use a wire mesh to heat a crucible to high temperatures. Instead, please use a clay triangle. Now students, let's first turn on our Bunsen burner. Now students, we will take our magnesium strip that we have over here, and we can heat it up with the use of a Bunsen flame here, and when it lights up, we will include our magnesium strip inside this crucible, and we will close the crucible so that the reaction can take place in a more controlled manner. So let's heat this magnesium strip up until it lights. And then we can provide it with heat with the use of a Bunsen flame like so, and we can allow this reaction to take place over a few minutes. So until this reaction goes to completion, we can take a look at another equipment, that is a mortar and pestle. What we have here is a mortar and a pestle. This is known as the mortar and this is our pestle. So the mortar and the pestle is used mainly to grind certain large particles of different substances and turn them into a fine powder. When you are using mortar and pestle, you are not supposed to lift the pestle and then drop it on the mortar. You are supposed to keep the mortar and the pestle connected to one another by placing the pestle gently on the surface of the mortar, and then you will be rotating it like so, gently grinding whatever that is present in the mortar. So to observe how the grinding action works, we have here a small amount of copper sulfate crystals. You can see how they look before we grind them, and we are going to take a small amount into our mortar here. We will leave a small amount in the watch glass. And then with the use of the pestle, we will start to grind this copper sulfate by taking the pestle in a circular path. We will start to grind the copper sulfate solid that we have in our mortar. You will apply some force when you do this to make sure that all of the solid is evenly grounded. Do not drop the pestle from a higher position onto the mortar. That is not how you should be using the mortar and pestle. Do not do this. It is not how you should be using the mortar and pestle. You should only be rotating it like so. And as you keep rotating it, you can see the copper sulfate crystals have now turned into a fine powder. When you need to take a fine powder into a reaction, you can use mortar and pestle to produce that type of fine powder for your reaction. Majority of the time, students, the mortar and pestle will retain some of the solids on the pestle as well as on the mortar, so you can actually scrape them using a spatula. And then there is a small spout here. You can collect all of your copper sulfate that we just turned into a fine powder. And if the powder does not come off the walls of the mortar easily, you can use a spatula and scrape those fine powders off of the wall of the mortar, and then you can transfer them into this. You can transfer them into another wash glass like so. See, there will be certain solid particles that are not going to be removed. There are going to be certain solid particles that are not easily removed from the surface. Then use a spatula and scrape it off the walls. There will be certain solids that will be quite difficult to remove with the use of a spatula as well. So at that point, you have to obtain whatever you can obtain from the mortar and transfer it into a different container. And then later on, when you're cleaning the mortar and the pestle, make sure to clean it thoroughly to remove all of the residual solids. Now, students, you can observe the difference between the two forms of copper sulfate. Copper sulfate crystals we obtain from the stock bottle, and copper sulfate that we just turned to a powder with the use of the mortar and the pestle. This is how we'll be using the mortar and pestle when it comes to grinding large particles of different solids into forming a powder. Now, let's remove the heat source from this crucible. After removing the heat source, please remember that this is a really hot crucible now. So you will have to use a forceps to remove the lid, or you can use the tongs to remove the lid as well. And then you can use a pair of tongs to hold the crucible. As you can see, the magnesium paste has completely reacted and turned into ash. What has happened here is magnesium paste has reacted with both oxygen and nitrogen, and as the oxygen runs out in this closed container, it will start to react with nitrogen to form magnesium nitride. So it contains both magnesium oxide and magnesium nitride here. So students, this is how we will be using the crucible and mortar and pestle. Over here we saw how the crucible was handled very carefully with the use of a pair of tongues, and when handling even finer objects we will be using forceps. And when you're heating a crucible, make sure to use a clay triangle so that we can directly provide heat to the crucible. Apart from that, we looked at mortar and pestle. You can see mortar and pestle was used to grind larger solid particles into smaller fine powders, and we learned about how to use it and how not to use it. So these are the main glassware and different lab equipments you will be mainly using in your lab. If you follow the instructions on how to use them correctly, if you make sure to follow the precautionary measures, then you can be safe yourself while safely handling the lab equipment without breaking them. So if you follow these instructions, you can be safe within a lab environment while making sure people around you as well as the lab equipment is also safe. So if you follow these instructions, you can use lab equipment such as the ones that we showed today for a very long time, and the quality of your experiments will also increase when you use them the way they are intended to be used. So students, keep these practices in mind when you are in the lab. Let's move on to learning how to use the triple beam balance. Triple beam balance for the first time. So let's learn how to use it. Before we use it, we have to identify the parts that is present in this triple beam balance. We have our base here, so everything that you see on this triple beam balance is present connected to our base. And here we have our stainless steel weighing pan. So we will be placing whatever the objects that we need to weigh on top of this weighing pan. And you can see over here there are 3 notched beams. The first notch we see here goes from 0 grams to 100 grams with 10 gram graduations. And we have our second beam. It goes from 0 grams to 500 grams with 100 gram graduations. And then finally, we have the last beam over here that goes from 0 gram to 10 grams with 1/10 of a gram graduation. When using the triple beam balance, we have to make sure the line you see over here, you can see a straight line over here, and on this part of the triple beam balance, you see a line with a 0 written next to it. So these 2 lines indicate us whether the triple beam is balanced or not. When measuring a mass using the triple beam balance, you have to make sure the 2 lines you see over here, should balance. The line that you see on the beam of the triple beam balance should align perfectly with the 0 line over here. When it aligns like that, it indicates that the triple beam is now at a balance. Now students, we have taken a look at how we can correctly use the triple beam balance. So now you have gathered information about how to use glassware in the lab and how to properly clean glassware, how to handle them safely, and what the precautionary measures revolving around each of the different glassware are. And after that, we have now taken a look at how we can use the triple beam balance to accurately measure different masses of different substances that you can find in the lab. With this, we conclude today's experiment, and we are going to be moving on to the next part of this experiment, where we will discuss different theory parts revolving around this experiment, as well as important questions that revolves around this practical 3. Now, let's move on to studio and discuss some questions, and we will take a look at further theory parts revolving around this experiment.